Dear friends, we sincerely thank everyone for joining our third workshop on large-scale holistic video understanding. I'm Vivek Sharma, welcoming you on behalf of our HVU Organization Committee. Before moving into the workshop, I would like to take a moment to say you happy June 10th. Our workshop focuses on learning a generic feature representation towards challenging holistic video analysis, recognizing scenes, objects, actions, attributes, and events in the real world. We also aim to cover important aspects of video recognition and understanding in this workshop, such as future frame prediction, large-scale video understanding, multiple category recognition videos, object and activity recognition in videos, weakly supervised object detection, unsupervised self-supervised representation learning, and 2D, 3D deep neural networks for action and activity recognition, and more. Our HVU dataset focuses on multi-label and multitask video understanding with approximately 572,000 trimmed videos in total with 9 million annotations for training, validation, and test set, spanning over 3,142 labels. HVU encompasses semantic aspects defined on categories of scenes, objects, actions, events, attributes, and concepts, which naturally captures the real-world scenarios. In our today's event, we have 5 prolific speakers. We tried to make our event inclusive by bringing community from both academia and industry. Here's our today's schedule. Each talk is approximately 40 minutes with last 5 minutes for question and answers. And we will also take a short break, 15 minutes break in between. Thanks. We now move on to our first speaker, Jan Kautz. Jan is a Vice President of Learning and Perception Research at NVIDIA. The title of his talk is Using AI to Perceive Humans. Thanks.
Hi, my name is Jan Kautz. I lead the Learning and Perception Research team here at NVIDIA, where my team specializes in AI-based perception. And today I'd like to talk about a few recent research projects on using AI to perceive humans. So, perceiving the human body is of great interest for many practical applications. For example, these methods can be used in humanoid robots that actually interact with humans, or for self-driving cars to understand their surroundings. You can also use them for monitoring humans, such as to automatically generate alarms in case of an emergency, or we could use it for sports analytics, where they can be used to create game statistics and personalized training and so forth. So, given all these different potential applications, we've spent quite a bit of time in this domain. In particular, I'd like to talk about 3D pose estimation from RGB-only images, and then how we can use that 3D pose to articulate a human body mesh. I will also show how we can deal with occlusions and moving cameras. And then once we know everything about the body, we will also estimate the 3D hand pose. So let's start with a 3D human pose estimation. And here, by 3D body pose estimation, I mean the localization of human body joints in the 2D image space, as well as in 3D with respect to the camera. Having a computational method with this ability has lots of practical applications. For example, at NVIDIA, we've been using it to let people stride across the moon surface, which was a demo a few years ago at SIGGRAPH, or in Omniverse Machinima, you might want to drive a character from a webcam's feed, for instance. So our goal is to train a model which of course is a neural network that takes an image of a pre-localized person, so we already have a bounding box in 2D, and then produce the 2D as well as 3D positions of all the body joints as the output. This is a very challenging problem, specifically the 3D localization part, because it's inherently an ill-posed problem. First, it's ill-posed because of the scale and the depth ambiguity. That is, there's many different 3D configurations that might yield the same 2D projection on your screen. So if you don't know the size of the person, it's hard to determine how far they are from the camera. Here's an example where there's two different scenes of a person with different scale and depth, but they project to the same 2D image. And this one-to-many mapping makes the problem very ambiguous. Second, in order to train a convolutional neural network, we need lots of training data. In this case, training images with accurate 3D pose annotations, because we want to predict not just the 2D locations in the image, but also the 3D world positions, or at least relative to depth in camera coordinates. Now, collecting such training data is actually really difficult and time-consuming because it requires sophisticated hardware setups, motion capture system, and the like. And as a result, collected data is often limited to controlled indoor environments. So they're not natural environments. As a result, it might not work outdoors. And of course, it's difficult to scale, right? How do you easily acquire lots and lots of people in such a capture setup? Now, there are two main approaches for training a pose network. One where you directly regress the 3D pose from an image. So you really go from image neural network to output the 3D coordinates of all the joints. Now, since such a model would be trained using very constrained images, such as the ones acquired in a motion capture setup, it's difficult for a network trained in such a way to generalize to unconstrained scenarios. Also, in order to reduce the 2D to 3D ambiguity, existing methods only estimate the relative 3D pose and neglect the absolute 3D translation of the person, because that's difficult to judge. Also, if you do it with this direct regression from image to 3D, it's really decoupled from the 2D image, if you will, right? You don't know where the 2D locations of the joints in the image are, so you can't double check whether they're sensible or not, the 3D ones. So it has some real downsides, this approach. Another possible approach is to train a model that first outputs just 2D locations of the key points, and then you take those 2D poses as input and try and lift it to 3D. 2D pose estimations work better, or can work better within the wild images, because we can label lots of 2D images by hand with 2D joint positions, which is difficult to do for 3D, right? Labeling in 3D would be really difficult for a human, but labeling the joint locations in 2D is actually quite possible. So as a result, such a method has a better ability or capability to generalize to unconstrained setups, because lifting something from just the 2D locations to 3D is independent of what the appearance of the image or video looks like. There's still some constraints or limitations, such as reproduction ambiguities are still difficult to deal with. For instance, in this case, we don't know whether it's the person is looking to the right and we're looking at it from the back, or the other way around, right? We would need to look at the image itself to determine what the actual orientation is. So our goal is to develop an approach that generalizes well to unconstrained environments, so arbitrary images and arbitrary scenes. We want to be able to handle some of the reproduction ambiguities, and we want to be able to provide absolute 3D pose so that the result of this pose estimation can be used for animation. So to this end, we've proposed a novel 2.5D pose representation that satisfies all of these requirements. So it's invariant to 3D scale and translation, so it's less ambiguous to estimate. We can exploit multiple sources of training data, that is 2D labels as well as 3D labels to exist, so it allows for better generalization. And it does enable exact 3D reconstruction to get absolute 3D pose. So our pipeline is as follows. We have an image, just RGB. We first estimate 2.5D pose using a neural network, and I'll explain what 2.5D means here in a second. We then devise an exact method to reconstruct the 3D pose from the 2.5D representation. And then we recover the correct scale of the person, which gives us our target absolute 3D body pose. Now, let's see what we mean here by the 2.5D pose representation. So here's the equation for perspective projection from 3D locations onto your 2D image. The capital X, Y, Z are the 3D coordinates of a particular body joint, in the case of camera matrix, and the lower case X and Y are the 2D projections. We represent the 2.5D pose using the 2D coordinates of the pixels in the image space. But then for the depth, we don't use absolute depth, but we use what we call root relative depth. That is, it's a depth value with respect to a particular root joint. And we get to pick which one we want to use. We usually consider the torso of the person as the root joint. And all the other depths of all the other joints are relative to the torso. Now, using this relative depth representation means that our 2.5D representation is really invariant to the 3D translation of the person, right? So it doesn't matter if you're closer or further away, because we're just recording depth relative to your torso and not relative to anything sort of outside of our control. Of course, we still need to make sure that it's invariant to the scale of the person to also reduce scale ambiguities. Now, for this, we do something very simple. We scale normalize the 3D pose such there is a fixed distance between a pair of key points, which brings all people to the same unit scale. So if a person is bigger, we make them smaller. If they're smaller, we make them bigger. Nothing, too surprising, really. Now, our final 2D pose representation looks like this. It consists of the 2D body joint coordinates, which are really well defined in the 2D image space, and then the scale normalized relative depth values, which are agnostic to the person's scale as well as to the person's translation. So as a result, it's significantly less ambiguous to estimate this 2.5D pose representation compared to an absolute 3D pose representation. Now, instead of predicting the 3D coordinates, the model predicts the 2D pose, so 2D coordinates in image space, and the scale normalized relative depths that constitute our 2.5D pose. Splitting it like this has the advantage that we can actually use two different sources of training data, which is really great. So first, we can collect, or take a collection of in the wild images that are annotated with 2D poses. So for each joint, we have the 2D location, and we know which joint is which joint. And this is fairly easy to do in large numbers because people can label these fairly accurately. Secondly, we can have a collection of constrained in-there images that also have 3D pose annotations, such as from mocap images, from mocap system. Even though they're hard to get in large numbers, it's good to have at least sort of some of it, right? Now, during training, we optimize for a loss consisting of two terms. One is the 2D loss to make sure that we get the 2D locations in the image space, right? And then we have a depth loss to estimate whether the predicted relative depth is accurate or not. Now, and for, and we sample an equal number of training images from both sources, meaning from the 2D pose annotations as well as for the 3D pose annotations. For images where we only have 2D pose annotations, we only compute the 2D loss and backpropagate through that. The depth loss is considered to be 0 here because we have no depth, right? And then for images where we have 3D pose annotations, we compute both losses, right? Because we can project the 3D onto the 2D image, so we get both the 2D coordinates as well as the relative 3D coordinate. And we can compute both losses and backpropagate the gradients through the entire network. Now, jointly training using both sources allows the model to be trained on very diverse images, and hence it leads to much better generalizability, which is what our main goal really was. So this is great. Now, we also want to look at the neural network itself that we use for the 2.5D pose regression. So yeah, typical regression networks often consist just of a simple backbone model such as ResNet 50 or the like, followed by a fully connected layer to give our desired output. Now, in order to keep the complexity of the fully connected layer tractable, often we need to make sure that the resolution of the input features are fairly small. So for ResNet 50, that might mean that it gets downsampled 32 times. To fulfill this, now this has a disadvantage to the model now. Immediately loses its ability to accurately localize body joints in the image because I've downsampled the spatial resolution. Now it can learn the overall structure of the body well, but the body joints won't be at exact 2D locations. So instead, to alleviate this problem, the state-of-the-art methods for 2D pose estimation resort to fully convolutional neural networks and predict the 2D pose using a heat map representation. So during training, we use the ground truth 2D annotations and create these heat maps by putting sort of Gaussian blobs centered at the true joint locations and supervise the network to produce these heat maps by a simple mean square error. So it's fairly straightforward. And we can do the same thing for the depth by creating sort of ground truth depth maps that have the correct depth value at the center of the Gaussian blob. Now, during inference, we get the estimated heat maps, and we take the 2D location with the highest value as the location of the body joint, right? It would be an argmax. And similarly, we can pick the depth value from the same location in the depth map. So that's actually fairly straightforward to do. However, it comes with a downside. In particular, the argmax operation is not differentiable, right? That means if you were to reconstruct a 3D pose from 2.5D, we can't apply any loss directly on the 3D pose, which isn't great. Not critical at the moment, but we'll see later on that it would be really useful to be able to do that. Furthermore, the ground truth heat maps are in effect hand designed, right? Because we're putting a Gaussian blob on them, which is not ideal because the spread of the heat maps is the same for all key points, where ideally it should be adapted for each key point, right? Heat maps should be very picky for places where it's easy to estimate the joint, such as for a wrist, right? It's relatively easy to pick out exactly where the wrist is. Whereas for the torso, it's much harder to pinpoint exactly where the joint should be. And as a result, the heat map should be, the blob should be wider for those locations. So ideally, we want to learn those instead of fixing them a priori. So to this end, we propose to learn the heat maps in a latent way and use soft argmax to go from heat maps to 2D joint locations in a fully differentiable way. So essentially, we take the latent heat maps produced by the network and apply softmax normalization to it and approximate the 2D coordinates with the highest confidence value via soft argmax, right? Fairly straightforward. For the relative depth values, we take essentially the Hadamard product of the normalized heat maps and the latent depth maps, which zeroes out all the depth values that we don't need, except for those that are close to the body joint, and then we just average those to give us the actual depth, which is simple to do. And that gives us the relative scale normalized relative depth for each of the joints. So as a result, we can now get a 2.5D pose from these latent heat maps and depth maps in a fully differentiable manner, which is an advantage. Furthermore, if you look at the softmax normalization formula, we see that there's a parameter that controls the spread of the heat maps after normalization. And in our formulation, we've kept it as a learnable parameter during training, which now leads also to an optimal value for each body joint type. So indeed, we can see what we already predicted should happen, that for joints that are easy to learn, it's a much more peaky distribution, whereas for other body parts such as the torso, we get a wider blob as a result, because it's a little bit more uncertain where the joint actually is. Now, this completes our full process for obtaining a 2.5D pose from an input image. So now we still need to go to 3D, right? Now, given the 2.5D pose, there's two more steps that we want to take, or that we have to take, to get our final absolute 3D pose, which is the 3D reconstruction from 2.5D and scale recovery. Now, to do the 3D reconstruction given a 2.5D pose, here shown in green, we need to find the depth z root of the root key point, here shown in red, in order to reconstruct the scale normalized 3D pose. Now, there's many 3D poses that can have the same 2D projection, which means we can plug any value of z root on the left side and it will give us some 3D coordinates on the right. However, given the relative depth and the intrinsic camera parameters and the knowledge that the distance between two key joints, it's a constant, there's a unique 3D pose that satisfies our scale normalization constraint, which leads to the following polynomial equation here, which we can just solve. Giving us a solution, or an exact solution for z root. So now we have everything to reconstruct the scale normalized 3D body pose. And this brings us to the final step of recovering the scale in order to obtain the absolute 3D pose. Now, for this, we need to know the 3D distance between the torso and the pelvis, which are the two joints I've chosen, and in many practical applications that can either be known in advance, or if it's not available, we can estimate it by assuming what sort of an average human, what the value is for an average human, or we can minimize sort of the bone lengths of all joints for an average human, and the resulting scale value brings sort of the bone lengths of the estimated pose as close as possible to that of an average person. So we can do it person specific or based on the average size of a person. And finally, this gives us our target absolute 3D pose. Now, in terms of accuracy, the method works really well, performs great on public benchmarks. It's published at a leading conference. However, there's still some challenges left to solve. In particular, as already mentioned, there are challenges around 3D training data. So, we started to think, what can we do to avoid the need for 3D annotations that come from mocap systems, which are really, really hard to get. So how can we train a model without 3D annotations? First, we identified that unlabeled multi-view data is a good source of data that can possibly replace 3D annotations for us. And it can be easily acquired in any setup with just multiple static cameras that you place, or even with a single moving camera around static people. So here's an example of our simple setup. It's very easy. We can even collect this alone. So this is here, a couple of cameras placed in Umar's home, who's the main author of this work. And he's recorded himself while doing some daily chores from 4 cameras in this case. So it's very easy to set up, and you can do this basically in the wild very, very, very easily for all kinds of use cases. Now, a simple way of utilizing unlabeled multi-view data for training is just via multi-view consistency, right? Instead of having ground truth labeled 3D data, we say, well, if you have multiple views, we want to make sure that our estimates are consistent across all the views. So, we process each camera view using the pose estimation model and supervise it to produce identical 3D poses from all camera views up to a rigid transformation, right? Because they are seen from different views. However, just naively enforcing multi-view consistency leads to degenerated solution, right? For example, Network can very easily cheat by just producing all zeros or a mean pose from all camera views to satisfy the multi-view consistency constraint. So that's, of course, not quite what we have in mind. Now, we avoid this problem by, again, adopting our 2.5D pose representation. So that gives us 2D pose and the scale normalized relative depth values. And as we mentioned before, the 3D pose can be reconstructed from the 2.5D pose, and this reconstruction process is fully differentiable. Hence, the multi-view consistency loss that we would like to apply can directly operate on the 3D poses because everything is differentiable. And then during training, we can introduce a 2D loss that enables correct 2D pose predictions. So it can't lead to degenerate solutions because we have some 2D data and it needs to be consistent with that 2D data. So for simplicity, let's just assume that 2D loss, the predicted 2D poses for each camera view are correct. And we only need to learn the correct relative depth values at this point. For this, we start to train the model jointly for both the 2D loss and the multi-view consistency loss. But since the 2D loss, the 2D poses are already correct, that was our assumption for a moment, the only way for the network to minimize the joint loss is to predict the correct relative depth values. Right? In addition, we used bone length loss, which forces bone length to lie in a plausible range and further constraints the solution space. So it's hard for the network to predict nonsensible things or try to cheat. And notably, we do not assume knowledge about the extrinsic camera parameters, right? In cases where they're known, that's great, we can use them. But if they're unknown, we don't need to estimate them explicitly, but we rather do this on the fly using the estimated 3D poses, and we align them using Procrustes analysis, which is super convenient, right? Because now we can just put down cameras. We don't need to do any extrinsic camera calibration. So it'll be done sort of while we're training the network. It'll figure it out on its own by using the rigid alignment process in the loop. So here we show results for in the wild videos taken from YouTube. Notice that it works very well. Even the relative distance between people when there's multiple in a frame is very good, right? Because we estimate as well as we can the absolute position of each of them. So if there's people further away, you can actually figure this out. And if there's people closer by, our method will automatically figure this out, which is really great to see. In terms of quantitative results, here's comparison to a bunch of different methods, all of them were state of the art at the time. On the human 3.6M dataset, which is a benchmark dataset used for human pose estimation, our approach yields 16 and 70% error reduction as compared to other semi or weakly supervised methods, which is great. We've also used the mannequin challenge dataset to train our method. So this is a dataset that contains people who are not moving, but the camera is moving around them or around them in parts or translates, which is really a great data set that we can employ. And if we use data from this training set to train our network and then run it again on a human 3.6M data set, we have also a reduction in error of 11%, which is a very good result. So in conclusion, we've presented an approach for 3D human pose estimation from single RGB images our approach does not require 3D training data, but instead uses unlabeled multi-view data for training, which makes our approach really very practical, in particular for scenarios where it's difficult to collect 3D ground truth data. This is a perfect method to use. Also, our approach provides absolute 3D poses and yields state-of-the-art performance. Now, I'd like to move on to mesh articulation. Here, the goal is that we want to articulate a human body mesh according to the 3D pose observed in an image. Most of the existing methods that solve this task, that's going from an image to a 3D human mesh, adopt a regression-based approach where an encoder with a fully connected layer predicts the parameters of some parameterized body model, usually the SMPL body model. Now, learning this sort of highly nonlinear mapping is quite a challenging task, and these methods often result in meshes that don't quite align with the image content. So it might be the pose might be roughly right, but doesn't fully align with what's perceived in the image. In particular, the feet and the hand regions are often quite off. This is very common for methods. On the other hand, as we've just seen, the estimation of sparse 3D key points of people works really well if you adopt pixel-aligned representations. Those can accurately estimate the body key points in 3D as well as the 2D projections that align with the image. So we propose to use this as the input, that is, use such a key point estimator, and then reconstruct a human body mesh from the 3D key point positions alone. So not going back necessarily to the image, but rather go from 3D key points to the mesh. So here's an overview of our approach. Given an RGB image, we first use the 3D key point regressor that provides 3D positions of all the body joints. In fact, we use the method that I just showed earlier. Then comma consists of, comma is our method, key point aware mesh articulation, consists of a series of simple and well-defined geometric operations that articulate a canonical mesh that has a skeleton to the target pose using the 3D key point positions only. So basically imagine if you have 3D key points, they are sufficient to compute the joint angles for a canonical mesh with a skeleton to pose this canonical mesh according to the estimated 3D key points. It's not entirely straightforward because we need to make sure that we deal with unnecessary twists, because those are ambiguous, right? From the 3D key points don't necessarily tell you how something is twisted or not, right? So we need to make sure we remove all unnecessary twists. But if you do that, it's very easy to get an articulated mesh just from the 3D key points. Now, while this already yields state-of-the-art, we show that these posed meshes can still be refined using sort of a simple first-order optimization that removes any remaining discrepancies between the regressed key points and the articulated mesh, and they can still be there before the optimization, just because when you pose according to 3D, there might be still some slight inconsistencies that you might want to get rid of. Note though that in contrast to all the other methods, our approach does not require training images with ground truth mesh annotations, right? All we require is a 3D key point regressor from which we pose the mesh. Now, one thing to note, we don't actually estimate the body shape, right? We only estimate the articulation of the mesh, not the body shape itself. Yet, this simple method offers significantly better alignment to the image content and achieves state-of-the-art on public benchmarks. Here's a list of methods that we compare against. Many of them do require mesh supervision, which we do not. So overall, we get better reconstruction error and accuracies. So here are a few qualitative results of complicated poses. You see the image and overlaid the mesh that we've estimated. This is on MS Coco. Here is a more example where we now rotate the meshes around so you can see how they actually look. And they're very sensible meshes that we've estimated. And here are some examples running frame to frame on videos. On the left is just a basic comma method, and on the right where we do the final refinement step. And as I mentioned, these are run frame to frame, right? There's no enforced temporal smoothness at all. And again, no mesh annotations were used to train this network. Again, another example. Even though it's only frame to frame, it's temporally, surprisingly consistent. Okay, finally, I'd like to talk about global occlusion-aware human mesh recovery. So all the videos you've seen so far were basically captured by a static camera, right? However, videos are often captured by dynamic cameras, and then reconstructing a pose in a global coordinate system can enable interesting applications such as VR, animation, and sports. But occlusions are a big problem in pose estimation. And if you have a dynamic camera, there's a lot of occlusions that can happen. For instance, a person might move out of the frame, or if there's multiple people, they might occlude each other. So we would need to handle those somehow. So our goal is to estimate the pose and the shape of people in a consistent global coordinate system from videos captured by dynamic cameras. So it's a very challenging problem. Standard pose estimation methods have real difficulty with videos like this. So here's an example of our method basically from that I just presented running on this video. Estimating accurate depth, very difficult. It's very difficult to estimate the global human motion from the moving camera. And it's difficult to handle severe and long-term occlusions. And you can see at the bottom that there's a lot of jittering, a lot of weird moving of people, estimated poses, because the methods don't know that the camera, or assume that the camera is static. So they don't know that the camera is moving. So as a result, they don't know what to do in that case. So to address all these issues, we propose an approach that leverages behavior generation models to hallucinate pose and global trajectories. So given an input video from a dynamic camera, we first pre-process the video. That is, we do multi-object tracking and re-identification to obtain the bounding block sequences of each person in the video. We then apply 3D human pose and shape estimation to obtain the motion of each person, which consists of the shape and the 3D pose sequence in camera coordinates for the part of the video that a person is detected. When there's occlusions, of course, we don't know what their pose or shape is. So the motion can have occlusions where poses for some frames are missing because the person is occluded, right? So in the next stage, we propose then to learn what we call a generative motion infiller to infill the occluded parts of the video and then obtain occlusion-free body motions. Then after that, we propose to use or to learn a global trajectory predictor that infers the global route translations and rotations of each person from the local body motion. So given the infill body motion, which is in local coordinates, we now predict a global trajectory for each person. And then finally, we propose a global optimization framework that jointly refines the trajectory of each person, as well as the camera parameters to match the video evidence, such as 2D key points. And so this global optimization ensures that the spatial relationships of the people in the video is accurate and consistent temporally and globally. Now, the generative motion infiller is based on a conditional VAE. So it essentially maps body motion with occlusions and the latent code to occlusion-free body motions. And we learned this based on a data set of human motions. So it's fairly straightforward to do. So the global trajectory predictor in our approach is motivated by the fact that the body motion of a person is really highly correlated with its global trajectory. So for instance, in this video, even though the human behavior is only rendered without translation, so it's we don't show you the ground plane or anything, we can still see that the person is walking backwards, right, and then taking a step to the left. It's very obvious to us. So as humans, we can hallucinate the global trajectory taken just by looking at local body motion. So we hypothesized that the same should be possible using a neural network that's trained for this task. Now, the global trajectory predictor we propose is also based on a conditional VAE. It essentially maps the collision-free body motion from the last step and a latent code V to the global trajectory of the person, including the route translation and rotations. So you really get motion, global motion out of this predictor. And then finally, we do this global optimization, where we predict everything jointly. We predict the camera poses, the trajectories, all making sure that everything is consistent between people as well. So let me show you a few results here. So you see input video on the top, and then bottom left is ours, and the bottom right is sort of a state-of-the-art method or baselines. If you stitch them together, what you would note that the baselines aren't meant or weren't really aware of the camera motion, so they're not expected to do very well. But the bottom left is our method, and whenever one of the meshes becomes transparent, it means that we had to infill the motion because it wasn't visible or it was included in the image. And you can see that even when sometimes the camera or the people are outside the frame, you can still estimate what their motion is. If the camera moves or stops or any of this, it's not a problem for our method. Or if they're only partially visible, we can handle all those cases and do something sensible. If you look at the top and at the bottom again, is sort of the baseline that you would get. And because we do this global optimization, at the end it's very consistent, temporally coherent. Even when there's occlusions, our infilled motions are very sensible. You can even tell that if you look carefully, you could even see that they were walking up the steps. It looked like they were walking up the steps and sitting down and so forth. So overall, it works remarkably well. Even some complicated motions like dancing, we can handle, even though there's always basically one person occluded. Right, with that, I'd like to point out the additional, or the work, the papers that this presentation so far was based on. So if you'd like to learn more, feel free to look at those papers. So in conclusion, I've talked about 3D pose estimation and how we can use it to articulate a human mesh, as well as how we can deal with moving cameras and occlusions. So thank you very much for attending my talk today.
Unfortunately, Jan couldn't join us for Q&As, but he asked me to ask you that you guys can reach out if you have any questions. And now we'll move on with our next speaker, Angela Yao. Angela is a professor at NUS, and the title of her talk is Segmenting and Anticipating Actions from Videos.
So my name is Angela Yao, and I'm from the National University of Singapore. It's a real pleasure to be here today to present some of my group's work on segmentation and anticipation. Right. So when we talk about video understanding, I think one of the hallmark tasks that we're used to dealing with is action recognition. And in action recognition, what we're doing is we take these pre-trimmed clips and then we classify it with a single semantic label. And the clips are relatively short. They're usually no more than a few seconds long. But we've gotten really good at being able to do this type of classification for thousands of classes, right? But if we consider the type of video feeds that we capture in real world data using video, like surveillance systems or autonomous vehicles or robots or so on, all of these are actually featuring video streams. So we don't have access to these tidy little pre-trimmed clips. And so our video of interest might occur over this longer time durations and also feature several actions in sequence, right? And these actions, they may or may not be related to one another, and they might have some temporal sequencing or relationships with respect to each other that might span beyond these few second long clips. And so in terms of video understanding, my group is really interested in analyzing these types of longer video sequences, especially with a sequence of actions. And so if we were to expand our consideration then from this pre-trimmed clip to the entire video stream or sequence, then it also gives us the opportunity to define some new tasks beyond the standard action recognition task. So one of these is temporal action segmentation, in which we want to identify all of the actions that occur in the observed sequence. So you can think of this as the temporal analog of semantic segmentation, but in time for actions. And also we can define a task of anticipation. So we want to anticipate actions that have not yet been observed. And to work on these types of tasks, we're going to consider a special type of video sequence, which have these multiple actions in succession. And these tend to occur very commonly in procedural activities. So these are videos of activities which are composed of individual actions or sub-activities that form some part of a higher level complex procedure. So here, this slide shows a little bit better defining what a procedural activity is. It's a task with some steps or some composing actions or sub-activities, however you want to refer to these, that follow some very loose ordering. So in this example that I'm showing here of someone making coffee, we have these 6 steps. But when we talk about the loose ordering, what I mean by this is that maybe the first 2 steps of filling water and grinding coffee, they might be exchanged in order, and this is still leads to the same making coffee objective, right? Furthermore, maybe something like lowering heat might not even actually occur in some sequences because maybe you're in a hurry and you just want to cook your coffee in the constant temperature throughout. And so this loose ordering definitely adds a lot of challenge for us when we want to model the temporal or sequential dynamics of the composing actions. So where can we find videos of procedural activities? A dominant source is on YouTube. So you get lots of these instructional videos. So if you were to search for making coffee on YouTube, you would get a video similar to this one.
Once the water is boiled, which is really important because a lot of people put just water inside of the bottom part of the stovetop espresso maker, and it can overheat the coffee and make it be really bitter. And then you put it inside of this little pot, and there's a little line underneath the bolt inside of it, and you fill it up. And then after you do that, you grind the coffee.
So this goes on, actually, it's about a 2 or 3 minute video.
It makes 2 normal sized cups of coffee or 1 giant sized cup of coffee. It's very thick. It's not too bitter.
But instructional videos are actually not the only source of procedural activities. If you also consider just the things that we do on an everyday basis. So here I'm showing an example from some clips from Ego 4D. These types of daily activities also have multiple steps. So things like doing laundry, washing your car, these are also procedural activities. So as I've already shown, working with these types of videos, it's challenging in terms of the semantics because of this loose ordering, right? And I'm not sure it actually came through, but these videos, they also feature a lot of background, non-relevant content. So in the one example that I showed, where they start talking about other things than the steps of making coffee, right? And so how to model these types of sequence semantics under this loose ordering, that's at the forefront of working with procedural activities. Additionally, there's the standard technical challenges of working with these longer video sequences. So we have to address questions like what types of network architecture to use, how to represent the input frames, especially as the video sequences get rather long and we're dealing with a lot of data. And on top of which, of course, because we have lots of data, then we probably have lots of labels. So how can we learn effectively while reducing these labeling efforts. So today I'm going to introduce some of our work in this area of segmentation then, and also a bit on anticipation. And in line with this last bit, we can start off with reducing the labeling efforts and learning effectively. I'm going to start with the one extreme, which is purely unsupervised type of segmentation. And when we started working on this, our rationale was that we wanted to be able to take a collection of video, for instance, of making coffee, and without any other information, can we find or discover the steps which are common, and then temporally localize these steps across this collection of video. So we opted to take an iterative approach where if you're given some initial segmentation, then you can learn some appearance model via clustering. And then via the clustering, and we can alternate then with learning the temporal sequence model of the activity, yield a segmentation, and then continue to repeat until you're left with the final segmentation. So this is the iterative approach here. Now, because we're working in an unsupervised way, the go-to is to take some form of clustering, right? But if we cluster naively in video, what you end up with are clusters which group according to the video itself, right? Because these appearances are much more similar rather than grouping by the action or the sub-activity. And so that's why it's necessary for us to introduce a discriminative clustering technique instead, so that we can encourage these frames to group according to their semantic similarity. And in addition, we also found that it was really important to explicitly handle the background or the irrelevant frames. One thing I wanted to highlight about this work was our sequence modeling. And what we did in this work was we treat the sequence as a permutation. So we then develop a probabilistic distribution, or we model the sequence with a probabilistic distribution over the permutations instead. In particular, we were using a Mallows model where the likelihood is defined as an exponential based on the distance between some canonical ordering and some observed ordering, along with this dispersion parameter, which can measure the distance, or basically it controls how much the distance will influence the likelihood. If we put all of this together, I don't want to go into too much detail here. The key takeaway here you can see is that our final appearance here is derived from some prior on the appearance, as well as the sequence or the ordering itself. And additionally, when we want to capture the background, then we add an additional indicator variable, which we modeled with a Bernoulli distribution to indicate whether certain frames are either background or relevant content. So we can have a look at some of the outcomes. So the video on the left was actually the example that I showed. So each color segment is indicating a different action, and then the black part is, which it's fast forwarding through, is background. So you can see that actually our background model is pretty good. We are able to discard most of it, but often we do sometimes mix up the action with respect to the ground truth. And one of the limitations of this, because we were working with modeling the sequence as a permutation, it really enforces a strict continual progression. So for instance, in the second video there, you can see that we're not able to model this repetition of this yellow sub-activity there that's shown on the ground truth. Okay. So the discovery scheme that I just outlined, it's based on the assumption that we have this entire collection of video, which is based on a single procedural activity. So the example I was showing was making coffee. But this implicitly assumes actually that we have this information that the video is of making coffee in the first place, right? And so what we wanted to do then is to say, well, you know what, this is some form of anything that I discover because I'm only looking at making coffee, then it's not going to generalize to other actions or other activities, right? Even though they might actually share some steps. So in this example here of coffee versus making chocolate milk from the powder, some shared actions like taking the cup or pouring the milk in, we're not going to be able to find these, right? And at the same time, we don't have too much knowledge we're not able to identify the actions which are exclusive to each other as well. And so because this unsupervised setting, here I put unsupervised in quotes now, is actually making use of this procedural activity label as is, why not incorporate this directly into the model itself? So that way we can formulate a discovery scheme which is global across all of the videos instead. And that's exactly what we do subsequently, where we incorporate an explicit classification objective onto this procedural activity label. So I don't want to run through too much detail of this work also, but because we're incorporating this objective, this classification objective of the procedural activity, we're able to discover these shared actions, or here we're calling them prototypes. So one thing I did want to highlight though is on the matrix on the right, this is a KL divergence of the discovered shared actions. And what we find is some very nice groupings of activities which have similar steps or actions. So for instance, like making drinks here of the coffee and the tea and the milk, these tend to share a lot of actions. So basically the color is indicating the KL divergence. So the lower the value and the closer to red, the more sharing there is going on. Another grouping here was cooking on the stovetop. So actions like, or activities like making pancakes or scrambling and frying eggs, we tend to find some of the common actions within as well. Now, so far, what I've talked about is unsupervised or supervision with this activity level label. I'd like to shift to the other extreme. So this is either within one or the other. So the other extreme I want to talk about is this fully supervised setting where you get labels of every frame in every video, right? And then on top of which we might have also a semi-supervised setting where we get labels of every frame, but only in some videos instead. So we've shifted from discovery now to just standard supervised learning, either full or semi-supervised. To do this, we decided to revisit this concept of encoder decoders. So these were fairly popular for temporal segmentation about 5 or 6 years ago, but they were superseded by the MSTCN, which are fundamentally different in that they maintain this fixed temporal resolution. So it's a WaveNet style of architecture with progressively larger convolutional kernels. But here we wanted to stick to this traditional encoder decoder with this shrink and then expand type of temporal resolution. And we thought that this type of architecture was more beneficial because the decoder very conveniently offers this inherent type of, let's say, multi-resolution in the feature representation. So as you progressively decode, you get a higher temporal resolution and also move closer towards your semantic label as well. So what we did was we opted to take this each layer of the decoder output and project it into the class itself, and at the same time upsample to the same length, and then just take a simple ensembling of this. So we refer to this as a course-defined ensemble. And in addition, we explored and then we merged the course-defined ensembling into a final output. We also explored a very simple multi-resolution max pooling strategy to do augmentation on the input features. I'll cover this a little bit later. I have some better visualizations to clarify what this is. But just these two simple, let's say, strategies of working on top of this encoder-decoder temporal convolutional network we found was really helpful. And it had a lot of advantages in terms of, one is reducing the over-segmentation, which the temporal convolutions are quite prone to, and therefore improving the accuracy. But also another nice finding was that we are able to reduce the overconfidence. So our networks are much better calibrated without this ensembling and feature augmentation. And so with this type of architecture, we're able to achieve state of the art on the standard benchmarks used for temporal action segmentation. The other advantage of this type of architecture is that there's a clear separation between the feature representations and the classification output. And this means that we have the opportunity also to do unsupervised feature learning. So we took this same architecture and proposed a contrastive learning scheme on top based on clustering, similar in concept to what I showed at the beginning with our unsupervised discovery work. And again, we're also leveraging this multi-resolution nature of the decoder to develop features to be used in the contrastive learning setup. And with that, we're able to learn features which are strong enough that we can apply towards semi-supervised learning. So if we only have to take 5 or 10% of the videos to be labeled, we can still be almost as competitive as the fully supervised setup. This, of course, also, so one is the strength of the features. And then the other aspect I'd like to point out is, again, because we're also leveraging the inherent redundancies present in video. But so far now, in terms of this semi-supervised learning, what I've shown, we're treating it purely as a learning setup or a learning problem, right? We can go a bit further by leveraging the inherent properties of the procedural videos themselves, right? So these procedural activities, as we said, they're composed of this sequence of the actions themselves. So if we just assume that for a given video, even though it's not labeled, it should share at least with at least one other video present in the data set, some common set of sub-activities, as well as the relative duration, then we can enforce this KL divergence with respect to this closest matching video. And this helps a lot with the learning for this semi-supervised setup. We can also go further and enforce a similar sequence ordering via dynamic time warping. And by doing so, we can then reduce the amount of fragmentation instead of freely allowing every frame to take on its own class label, which is the standard formulation. It's a per frame classification task. So far, I've introduced these 3 settings: unsupervised, fully supervised, and also the semi-supervised. I want to move on to a final weakly supervised setting in which we give the labels of some frames of some videos. And now here, actually, because we're treating each video as a sample, this is why we consider this a form of weak supervision rather than semi-supervision, right? So because each video is a sample and I have only some frames labeled, then this is a weak label in comparison to the full label of the entire sequence. And again, we revisit a fairly classic setup here, where we decided we wanted to be fairly principled in how we model the sequence and just handle these unlabeled frames as part of a EM framework. And using EM is actually quite beneficial because we can also retain soft labels then to all of the frames, especially the ones which are unlabeled, which we found also gave us a lot of flexibility and also improvement in performance. So if we consider some sequence segment bounded by any 2 labeled frames, that's what I'm showing on the dark blue and the dark yellow lines, then we can formulate the likelihood of that segment simply as the product of all of the frames up to some unknown boundary as sub k, as having the same label as given in the dark blue, and then similarly for all of the frames to the right of that boundary, following the same label as the t sub k minus 1. So the right given frame annotation. And then we can iterate over all of the possible boundaries, okay? So this is showing just one possible location now. And on top of which, actually, we can iterate over different cases of the possible segments. So here, over the 2 different labels given, let's say both labels are the same. Then there's a situation where there's no boundary in between. There's a situation where the 2 labels on the 2 ends are different. This one I already showed with a single boundary in between. And for these 2 cases, maybe there's actually 2 boundaries in between, and so on. For each of these, we can iterate the likelihood and define a combined Q function for the EM. And with some rearrangement, actually, the Q function very nicely simplifies to a frame-wise cross entropy. And so we can iteratively estimate then the individual frame weights of omega based on some current neural network parameters, and that's the expectation step, and then maximize the Q function as part of training the network itself. And this is the maximization step. So with this type of formulation, we find that the approach is pretty competitive in segmentation, but also flexible in the sense that we're not assuming any structure to the labels. So in the previous slide, actually, I only showed 3 different cases, right? We've opted only to enumerate up to these 3 cases, which we think cover the majority of the situations we want to handle. But this is only out of simplicity in the sense that the framework itself is general enough to handle more situations as well. And the last point, of course, is that because we're adopting this probabilistic framework, the overall system is robust in terms of handling the missing labels. If we consider that there's some segment missing in between, the formulation is well designed to handle this setting. Okay, so now I want to switch over from the temporal segmentation to anticipation. And so this is where we observe some part of the video sequence, and we want to predict some not yet observed actions coming up. And so this is action anticipation. And for anticipation, there's actually a couple variants of the task. One is the next action anticipation. We just want to anticipate the semantic label of what's coming up. And the other is dense anticipation, which you can also consider as a form of segmentation of the future, let's say. Where we want to predict not only what will happen, but also for how long into the future. And in the context of our discussion earlier on the technical challenges of working with these longer streams of video, we were aiming to then develop an architecture here, which would be flexible enough to allow us to explore different temporal resolutions, as well as different levels of input abstractions, as well as different temporal extents, whether it's from just a little bit of the previous observation all the way to everything that we've observed up to that point. So with all of these considerations in mind, we develop an aggregation framework built up from 2 different types of blocks. One is this coupling block that I'm showing, where we take the observed sequence and we want to summarize each segment of the sequence. So here, what I'm showing with the different colored blocks is actually the semantic label of that frame. And we're going to simply summarize each segment with a simple max pooling. And then merge these into one feature here, this indicated by S. So this is applied to the entire observed sequence. This is what we call the spanning past. And we do something similar with this recent past. And these 2 then get merged together or coupled together into a block using attention reweighting and so on. So I won't go into the full detail settings here. And then we repeat this at multiple resolutions for both the spanning past as well as the recent past. And so for each of these resolutions, they have their own coupling block that merges them together. And finally, all of these get aggregated into a temporal block, right? And we repeat these for the different combinations as well. So this is the temporal aggregate block for each of the recent past scales. Sum these up, and then this forms some general representation for the entire video, which we find is flexible enough to do our intended tasks of next action anticipation, also the dense anticipation. But with a few modifications, we can actually use this to incorporate the entire video as well, not just the portion up to the observation, to handle the more traditional tasks like action recognition or segmentation. And we found that this worked especially well at the time for anticipation as well as recognition for working, for instance, on the Epic Kitchens dataset. And I want to highlight one experimental finding, which where we varied the extent of this spanning past to basically answer this question of how much past temporal extent do we really need to perform this anticipation task. And for the 2 data sets that we were considering, one was the breakfast actions shown on the left, and then on the right was the Epic Kitchens. We found that basically that using this entire past of the sequence is beneficial for breakfast, but not so much for Epic. And the performance stays more or less flat. You can see across the the time axis there. And our interpretation of this behavior was that basically because the labels in Epic Kitchens are quite fine-grained, and also the median duration of the action is quite short, only a couple of seconds. So over the span of say 30 seconds or so, we might observe 15 or 16 actions. It gets to be too difficult to link together without better temporal sequencing, sequence modeling, or some explicit sequence modeling, which we don't have here in this model. On top of which, we also believe that there's insufficiency in terms of the data, in terms of the number of classes and number of samples. So if we revisit the questions that we started with on looking at these different looking at segmentation and anticipation in these long sequences, what types of network architecture should we use? Our findings are that basically we should take advantage of multi-temporal resolution and multi-temporal scales, as well as this ensembling effect. Additionally, we found that if we separate this representation learning and the classification, this adds flexibility for reducing the amount of labels that we might want to incorporate. How to represent the input frames? What we found effective to be is just some local pooling. Again, this pooling over multiple different scales to capture, let's say, different windows or segments. And then finally, in terms of reducing the labeling efforts, to leverage the inherent properties of the videos themselves. So the fact that we know that there is a sequence of various actions. And finally, to also leverage the redundancy of videos. So even the sparse frame-wise labels of some videos of the full data set is sufficient to capture what we want to for learning. So for the last bit of my talk, I want to transition into a bit more application orientation. Why are we interested in looking at these procedural activities? And one application setting which we're interested in is this idea of having a smart assistant. So maybe some sort of situated agent sitting inside your smart glasses, and they might communicate with you as you're doing some complex task, right? So whether you're cooking or assembling furniture for you and I, or maybe you guys are doing some plumbing or home repair, or even more, let's say specialized tasks like handling machinery or medical procedures and so on. So with each of these settings, the idea is that basically you want your assistant to be able to recognize what you're doing, anticipate what's coming up, and then also provide you some support, right? So telling you what tools you might need, what actions you should take, and give you feedback whether you've done something correctly or not. And to help us in service of this setting, what we've done is we've designed a toy assembly problem to encapsulate this objective. So here we're working with these take apart toys. So they're about 15 to 25 pieces. They require about 5 to 10 steps to assemble or disassemble. And the nice part with these toys is that they can actually be put together in varying orders, right? So in this case, I could start with the body or the chassis of the vehicle, but I can also start with the arm or the wheels. It's up to the individual who's putting them together. We recorded a large-scale data set of people putting together and disassembling these toys. It's a multi-view data set from both static and egocentric points of view. And then we label the different actions that's happening. So we define 2 granularities of action labels: fine actions, which involve basically contacting a single part until the point that you release that part, and then coarse action labels, which, let's see if it plays, yeah. So these coarse actions are composed of several of these fine-grained actions put together, grouped together in service of one attaching or detaching of a specific component in the toy. And one neat thing that we observed actually after we had recorded all the data was that there were lots of instances where people would make mistakes. Because in this setting, we didn't give them strict instructions, right? We wanted to have this sequence variation. So we just gave them a picture of the completed toy and told them to assemble it. I mean, the toys are designed for 3 years plus, but yeah. So what we observed is that actually people make a lot of mistakes also. So in this example here, the girl, she's trying to put on the cabin of the vehicle, but she's forgotten the seat to put in the seat first, so it doesn't fit. So she has to go back, detach the cabin, and then put in the seat before it can go on. And now it works. And so this was one really interesting thing that came out after we observed this after we recorded all the data. So we decided to go back and label all of these as well. So we end up with these 3 levels of labels: fine actions, coarse actions, as well as the mistakes and corrections. On top of which we also added the 3D hand poses as well, and the 3D hand shape in service of being able to do action recognition from pose-based inputs. So not just the RGB inputs as well. So we're also presenting this data set here at CVPR, the main conference. So if any of you guys work on either action recognition or also pose estimation, I encourage you guys to go and have a look. We're presenting it on Friday in the main conference. And we'll also be offering some challenges associated with the data as well. And so with that, I'd like to conclude by acknowledging all of the students who worked on the several works that I presented today as well. And with that, I'm happy to take questions. Yes.
Hi, thanks for the talk. I have 2 questions.
Mm-hmm.
The more important one is that in a lot of these videos, there's already a little bit of cameraman bias that exists. So for like action recognition, if you look at, for example, more classical data sets like this, like there is a cameraman actually tracking the thing. And even these instructional videos,
yes,
especially the egocentric ones, it's kind of looking. So how do you, how do you design models that can learn from videos which are more like surveillance type videos, where there's a lot of things are happening at the same time? And, because in my experience, a lot of these methods actually fail on such in the wild kind of videos.
So I think the bias from the camera itself, it's definitely present, especially if you're dealing with these instructional videos, which are like in that one example I showed, this is even a pre-produced, right? And I think that's one of the reasons why we're so good at being able to isolate that background. I think where you can make up for some of this is in the temporal sequencing itself. So if you look at the way that our action segmentation task is currently posed, we do have so-called background, but depending on the variant and the data set that you're working with, sometimes this background is not even considered, right, which significantly simplifies it. So I think in the case you're talking about in terms of the surveillance, I think you have to incorporate this into your temporal modeling, that you have much longer durations of background and that this background occurrence is much more random rather than what you would expect in a pre-produced video, right?
My second question is, you mentioned about like the go-to approaches like clustering when you're trying to segment videos, but they tend to segment scenes from the same video rather than based on the activity. So, are there any data augmentation schemes that you can apply so that it will pay more attention to the activity rather than the fact that they're from the same video?
That's a good question. So the question is asking basically, if the go-to approach is to use clustering, how do we avoid this appearance, clustering based on appearance, right? So I want to qualify that actually. We want to use clustering when it's fully unsupervised, right? Unsupervised learning, the go-to is to do clustering. But I think once you have some knowledge of the labels, even if it's just a few frames, I don't think that clustering is necessarily the right approach to take anymore. But that having been said, I think a lot of this has to do with the feature representations you're using. Clusters end up based on the videos themselves is because we're relying heavily on the appearance features, which each frame of the video looks too similar to the next, instead of encoding the actual semantic information. But if we had features which are high level enough already, then I don't think that would happen necessarily. So it's really depending on what inputs you have. Yes.
Yeah, I have a question. In one of the videos, especially YouTube videos, people are talking. I think consider language in performing this part.
Yes, absolutely. So the question is, in this example that we showed at the beginning here. Oops. Oh, sorry.
Boil water.
They talk, right?
And then
So,
giant kettle.
Here she even says, oh, sorry, that was the end. Maybe we can let the next speaker set up while I'm answering a question. Yeah, so she even says, you know, you should boil water while you're setting up the kettle, right? Absolutely. So taking advantage of the text or the narrations is a great indication. There's lots of works, which I would say I didn't properly acknowledge in the related work section to use as a form of weak label. One of the challenges of doing this is that, of course, that they don't only talk about what they're doing. They talk about a lot of background stuff. So in this clip, I didn't have time to show the full clip. In the middle, she starts dancing around and talking about how she likes to drink while she's waiting for the coffee to cook and so on. So, you know, there's these additional challenges also. So you get some information, but there's also, you also have to be prepared to handle or to be robust enough to handle all of it, right? So the fact that one, they start talking about things that are not relevant, and two, also what they talk about sometimes are not aligned with what they're actually doing. And so these are additional challenges there. Yes.
Hi, so I have two questions. One, both of them are about predicting the future action.
Mm-hmm.
So from what you showed, it resembles a lot of like language model. And I thought to ask if maybe you tried some of these techniques and what did you find about it? And second, when you do the pooling, how to incorporate the length of each segment or the whole video into the prediction model?
Okay, let me repeat this question. So the first question was asking, basically this sequence dynamics, it seems like we could benefit from language modeling, right? And you're absolutely right. So this Mallow's model that I showed for the unsupervised, for instance, this has also been used in language modeling as well. And I think for anticipation, so we haven't done it ourselves, but definitely others have done, and it turns to work out well as well, definitely. For the second question on the pooling, the whole point here was that we didn't know what the right scale to pool at should be, right? So that's the whole point behind the ensemble, is that we should just pool at different temporal scales or different, let's say, segment lengths, and then rely on the method to leverage the whole ensemble and discover what is most beneficial. And usually, because it's an ensemble method, you get improvements as you just add more and more scales anyway, right? There's no, because we don't want to bother having the trade-off to say, I want to select the perfect window length, and that's going to be the most beneficial, right? Because maybe that works for this data set, but for the other data set, it doesn't, right?
If I can continue, because you also show that you predict the length of the future action and not only. So would it be wise to think it's dependent also of the length of the previous action? Like if the video narrator is slow working, then obviously the future action can also be slow.
Yes. So these are all cues that you can incorporate into the whole, into the scheme as well. I think there's a question in the back.
Professor, for your nice talk. So I have a question, like, did you actually explore the composition of the power of the network? So by compositional, for example, your first video, you're making coffee. If you don't heat the coffee, then it's just boiling the milk. Did any of the work, or did you actually try, like, these fine-grained actions is actually telling a story? That, did you actually try to get that story, like that goal, or like, let's say we are giving two compositions during training, and in the testing, the composition is different, and it's telling a different story. So did you explore that part of the composition of thought?
That's a great question. So the question is basically asking, you know, there's a compositional nature to these individual sequences, individual steps, right? And depending on the content of the composition, it becomes different actions, right? Did I understand you correctly?
Yeah.
Yes. So I think We didn't do that explicitly. The closest would be in this semi-supervised work I showed, where we match it to one other video. So we don't try to summarize this composition for that entire activity as a whole to say, it has to be like this. Instead, we just match it to the nearest one. So in my pool of videos, as long as I have one other video, which it shares the most similar composition, and then we try to minimize the Kullback Leibler divergence between these two. So that's it, but that's more on a sample specific basis. It's not related to the overall activity itself, but you can definitely do this type of top-down modeling as well. How are we doing for time? Should we? Okay, great. I'm happy to take on further questions later on. Thanks, everybody.
Now, we would like to invite our next speaker is Elizabeth Science.
All right, let's get started. So yeah, today I'm going to talk about learning representations for solving holistic video understanding. And specifically, I want to focus on this robustness aspect in learning representations. Great. So we all love getting inspirations from Hollywood movies. And here I'm showing a short clip from the movie WALL-E. I like this clip partially because it shows several sophisticated computer vision tasks as well as robotics tasks. It shows this localization task, processing noisy, low quality video input, human detection segmentation, pose estimation tracking, all the way to the learning the concept of learning dancing in a one-shot demonstration scenario. And then it goes on imitation learning. So as we watch this, I'm pretty sure that many of you have a pretty good idea on how to tackle maybe one of these tasks or a few of these tasks. And as a community, I think I'm pretty sure we can build a computer vision system that can kind of mimic this scenario. In fact, we've made a great progress as a community on a bunch of different video understanding tasks. And all these tasks share this common goal of performing holistic video understanding in the end. But we tackle these subproblems in the hope, each of these subproblems in the hope that one day this will all make sense. But in a way, the current practice is like building an assembly line in that we have multiple different components, each tackling very specific tasks almost independently of each other. And this means we are building an army of highly specialized domain experts where each model is really optimized to be good at just a single task. And the way that I see this is like viewing the world through a straw, because the learned representations contain just enough information to solve a specific task. And I really like this motivation of this workshop, partially because it encourages us to move beyond this current practice and move toward building a holistic agent that can understand the video content in a holistic manner. So how do we get there? I think it's $1 million question that we all have. Well, one possible solution, I think, might be to build this multitask agent that shares a single body, single brain that has some general representation of the world, how the world works, combined with different multiple hands, each tackling different tasks based on this shared representation. And this idea is already making great progress in the community. We have models like Omnivore from Facebook and Gato from DeepMind that learn this single shared multimodal model for processing this multiple modalities and multiple tasks all simultaneously. And I think one benefit here is that it significantly simplifies the training setup. I mean, think of having to train a single model versus 10 different models, each with different architectures, learning rates, optimizers, etc. The simplicity here is particularly helpful because, well, we know the scaling law. A couple of years back in NLP domain, there was a paper that shows the language modeling performance improves as we increase the model size, data set size, and the amount of compute. And this year at CVPR, there's a paper that essentially shows the same thing works in the vision domain. But there's one caveat, and that's to the main part of the talk. The current models learn less effectively from noisy and uncurated data sets compared to well-curated data sets like ImageNet and Kinetics. Here I'm showing a plot that essentially shows a model that was trained on Kinetics, which is well-curated, performs just as good as another model that have seen 5 times more samples, but in an uncurated, noisy scenario. And to me, this is a disappointment because one of the most crucial components in the scaling law, which is large scale data, it will inevitably come from this noisy in the wild setting in an uncurated manner. And this means we need a robust models and algorithms that can fully leverage this noisy large scale data. So here's the main theme of this talk. I want to focus on the robustness aspect in learning representations and try to answer these 2 questions. First, okay, we have this noisy, uncurated, large scale data. How can we learn robustly from such data? And 2, how can we encode noisy data robustly more from the architectural perspective? So for the first question, I'll present our recent work, which will be presented at this conference, which proposes a new contrastive learning loss for self-supervised learning that can learn robustly from noisy, uncurated data. And for the second question, I'll present another work that will appear at ICML this year, which proposes this new self-attention mechanism that can robustly encode input data under various noise and corruption scenarios. So let's dive into the first part. This is a joint work with Qingyao Chuang from MIT, along with several colleagues at MSR and MIT. So to set the stage, let's first talk about what contrastive learning is. It essentially learns representation of the data by aligning views. And specifically, the learning objective here is to discriminate semantically related pairs of views of an instance from the unrelated pairs of views. And the grand assumption here, obviously, is that the positive views will share certain common information about an instance. Well, how do we get it? In the case of the images, we can apply standard augmentation techniques like cropping, etc. And in the case of the video, we can also take neighboring frames and clips, or maybe use the corresponding optical flow, or in the multimodal regime, we can use co-occurring audio and text. But in reality, this assumption about the positive views will share a common information can be invalid. For example, in the image domain, as you can see in the image here, different croppings from the same image can capture a very different objects. And this issue, in the context of this workshop, we all know that it will get worse for cross-modal video contrastive learning scenario, because oftentimes the audio doesn't really capture, what's happening in the view with the background music, overdubbing, etc. And in the case of the caption, especially when it's automatically transcribed from speech, then there is, finding this very correct alignment between video and text becomes an issue. And there are several papers that report that models struggle to learn from such misaligned views. How do we deal with that? One common strategy is simply to avoid them as much as possible. And for that, we can carefully design these view sampling strategies using our prior knowledge. For example, in video, the nearby frames tend to contain similar content. So we can take them as positives, and distant frames, well, because it happened in a distant future or past, they might contain negative views. But it's easy to see that it's fairly difficult to find a generalizable solution. What if there's a video working out at a gym? someone doing repetitive motion, then even though the distant frame, you take it as a negative, it may actually contain the same thing. The second idea, which we use in this work, is to embrace the noise. But we developed this robust learning algorithm that is just naturally robust to the noise. And I think this is promising, especially in the large scale regime, because the first approach, I'm a little skeptical in that, it's difficult to find a generalizable solution. If we have a learning algorithm just robust, then I think this is the path to the large scale learning scenarios. Okay, so what's the main idea in our work? We treat the noisy views as the noisy labels, just as in the classification. In fact, the info-NCE loss, which is popular in contrastive learning, is essentially a K+1 way classification objective solving this instance discrimination task. And once you take this view that noisy views are noisy labels, then we can start thinking about, can we extend this robust classification loss functions? Now, there exists this vast literature on learning from noisy labels in the classification scenario. So can we take one of those and maybe extend it to the contrastive learning scenario? So we focus on this family of loss functions that are called symmetric losses. There is a previous paper, Vishy et al. From NECO 2015 that showed that these symmetric loss functions have a strong theoretical guarantee against noisy labels in the binary classification scenario. Essentially, what they proved is that they proved minimizing a noisy risk in the presence of the noisy labels approximately also minimizes the clean risk. So what is a symmetric loss then? It's simply the symmetric loss. We call a loss is a symmetric if the loss sums to a constant for each class. So you can easily see that, for example, the exponential loss is symmetric, but the softmax loss, which is used in the info-NCE, is not symmetric because the positives and negatives are intertwined in a single loss formulation. So in this work, we propose a robust info-NCE, which is, in short, rinse. It looks like this, and I'll get into it slowly. The first parameter that you want to look at is this Q. This is a hyperparameter that you set beforehand. So the Q value controls how the loss should behave when it sees the noisy views. So when the Q equals 1, then you can easily see that it's a combination of K+1 exponential loss functions. So it fully satisfies this symmetric condition. And then it also leverages this strong theoretical guarantee against noisy views. When on the other end of the spectrum, when Q is 0, then rinse is actually asymptotically equivalent to info-NCE. When you actually sit down, compute the derivative of this loss function, then you will see that these are, rinse and info-NCE, they're actually equivalent in the gradient space. Okay, so let me try to sort of demystify this theoretical aspect and provide some intuitive explanations on how rinse provides robustness. And we can perhaps start with how info-NCE behaves with noisy views first. Here we can visualize the loss values in this heat map representation, where the x-axis shows the positive pair score and the y-axis shows the negative pair score. And just to simplify the analysis, here I'm assuming that there is a single negative and single positive views. And as we would expect, we have the lowest loss value, dark red, at the top right corner. Well, because we want the positive pairs to score higher and negative pairs to score lower. And similarly, we have the highest loss value at the bottom left corner. Okay, so this is all obvious. We all know this. What's interesting is in the gradient space, the cross entropy loss actually puts exponentially higher weights to samples that incur high loss values. So it's towards the bottom left. And this is good in the clean view scenario because it's implicitly performing this hard sample mining automatically, which can help accelerate the convergence. But we all know that the noisy views, they tend to incur high loss values. And this can be problematic. Here's why. They incur high loss values. And in the gradient space, we are putting exponentially higher weights to potentially noisy views. So in a way, the gradient can be dominated by noisy views. So this is exactly what we're trying to avoid. So let's now look at how rinse behaves with noisy views. Well, in the limit of Q approaching 0, we've seen that this is info and C. So when Q equals 1, we have quite different loss and gradient landscapes. The biggest difference that I want to highlight is that we put exponentially lower weights to samples that incur high loss values. And this means that the loss is playing conservative to potentially noisy samples. And as we interpolate Q from 0 to 1, we are controlling essentially, hey, rinse, determine how conservative you want to play when you see the noisy samples. And by the way, I've been plotting these gradients only with respect to the positive views. So let's see how rinse behaves with negative views. Unlike the positive gradients, where we put more emphasis on the easy positives, we put more emphasis on the hard negatives, just as how the info NCE works. So in a way, we are performing a easy positive mining because they could be noisy, and hard negative mining. And this design decision is good, especially in the contrastive learning setup, because you tend to have a much smaller number of positive views, oftentimes 1, versus negative views, you have hundreds of negative samples. So a single noisy positive view can screw up the training. So that's why we are trying to be conservative to them. But in the negative case, we have many samples, and hard negative mining in general helps convergence. So that's how the design, how the rinse behaves in the gradient space. So let's see some numbers. We tried this loss on a standard ImageNet classification scenario where we pre-train a model from scratch using contrastive learning and then test it on the ImageNet test set. And here we take the official implementation of SimClear and Mocha v3 and simply replace the info NCE objective with our rinse objective. So all the other settings like data augmentation, optimizer, they are all identical. And in both cases, we get about 1% performance improvement. And we didn't expect this, but this was interesting because it means the standard augmentation on ImageNet can actually introduce noisy views. And here we show some of the positive pairs generated by the SimClear object augmentation pipeline. And below each pair, we are showing our positive score prediction. As we can see, some positive views are actually quite noisy. And we can see that the scores below show that the model can reasonably predict that they are not that similar. Now, info NCE will put exponentially higher weights to these views, whereas in the rinse, we are just putting less emphasis on those. And that's where the robustness comes from in our formulation. We also tried this in the video scenario. We do audio-visual contrastive learning on Kinetics 400 and then transfer that to UCF and HMDB. And here we also observe, we take a cross-avid baseline, which was presented at CVPR last year. And again, same thing, we replaced the info NCE with rinse. All the other things remain the same. And we already improved the performance by about 2%. So these results are quite encouraging. And the natural next step is to test this in the large scale in the wild setting, where the expected noise level is higher. So for that, we used the archive 100 million data set, which we released at last year ICCV. It's a large scale data set of 270,000 hours of video. And to construct this, we started with 9 million random videos, and then we solved this constrained optimization problem that tries to find a subset that will maximize the mutual information between two modalities, audio and visual. So for example, as a result, this subset that we constructed will try to discard music videos unless there is a high mutual information between the audio and visual signals. But this data set is still noisy because unlike existing like a kinetics data set or audio set, this data set, nobody actually looked at what samples there are. No, it's not validated, it's not labeled, etc. So using the archive 100 million data set, we did the audio-visual cross-modal contrastive learning. And the plot on the left shows that we tested this on different subsets with different sizes from the archive 100 million. And the plot on the left shows that the rinse scales better than InfoNCE as we increase the data set size. And on the right, it shows that in terms of the convergence, rinse also converges more favorably to the InfoNCE. I will skip this slide except to just highlight that we also tried the same thing on the graph contrastive learning, and it tends to improve the performance. But I do want to highlight that implementation of rinse is actually a single line change, as you can see in this pseudocode. And the code is open sourced. So if for your next contrastive learning project, maybe you can try this, especially when you suspect that there might be some noise in the data. Okay, so that's what the first part is about. So let me move on to the second part of the talk. That is, how can we encode noisy data in a robust manner from the architecture perspective? So this work is a joint work with Baifeng Shi from UC Berkeley, along with our colleagues at MSR and UC Berkeley. And here we are presenting a new self-attention formulation that can robustly encode data under various noise corruption scenarios. So we know that attention plays an important role in our vision systems, in our human vision systems. For example, if we look at a picture of a human face, our eyes tend to first land on the eyes, and then nose, and then to the mouth, and then maybe hair, and then the overall contour. And this is well known by eye tracking and numerous series of experiments, human experiments in the cognitive science literature. And it's also well known that this attention is the key to human vision systems in a way that we observe this very high dimensional signal, but somehow we can very efficiently process all those signals. And that could be coming from attention because it allows us to focus on regions that matters to you. And inspired by this, obviously, modern neural networks like transformers, they also adopt attention as the key design component. And their attention maps tend to showcase the salient regions in the input data. And recent work also suggests that self-attention may help transformers improve the model robustness. The plot here shows that when you scale up the vision transformers in terms of the model size, they tend to provide better robustness compared to when you actually scale up the resonance in the same manner. So despite the progress, the current attention designs in the neural network are still far from being perfect. For example, they are not still robust enough under different kinds of image corruptions. And we all see that the adversarial robustness, all that literature that suggests that we are far from this human level robustness in processing visual input. When we actually look at the self-attention maps, we can also see that sometimes they show they highlight regions that are not very interpretable in a way that when you look at the eye tracking data and then do side-by-side comparison, I can see why eye tracking is highlighting certain region. But in certain cases, I'm not too sure what's going on in the self-attention maps. So motivated by all this, we're proposing a new self-attention mechanism called VARS. It's short for visual attention by recurrent sparse reconstruction. The design of the VARS is inspired by two key features in human attention: recurrency and sparsity. And this new module can be easily incorporated into modern transformer networks, as I will show later in the slides. And eventually, we want to show that VARS improves the robustness under various noise corruption scenarios. And I also show that the self-attention is actually a special case under the framework of the VARS. So let's jump in. Let me motivate why recurrency and sparsity. At a first glance at this image, you will see a bunch of bars just randomly scattered, each with the same intensity, oriented in a random manner. But as you keep staring at it, you will notice that some bars like this suddenly popping up to form continuous curves, almost creating this visual illusion. And then your attention is fixated on a much sparser set of bars all of a sudden, almost ignoring all the other bars that really don't form any meaningful pattern. So how does this happen in our brain? The cognitive science literature explained this using the concept of recurrency and sparsity. In fact, the various studies show that the ability to detect salient patterns is highly related to these horizontal recurrent connections between neurons within the same layer in our brain. So suppose a set of neurons, each being activated by different orientations. When the brain processes this image, the neurons go through this recurrent process where they either excite or inhibit each other. For example, if two neurons represent similar orientations, they tend to excite each other, as shown in the green arrows, because they are more likely to form a curve. And if the orientations are almost perpendicular to each other, then there will be mutual inhibition, shown in red. And this horizontal recurrent connections in a layer have shown to help amplify the salient regions, patterns, and repress the noisy signals, ultimately leading to sparse attention region. In the neural network, the standard feed-forward layer, we don't have the concept of recurrency. So let's see how we can add this concept of recurrency to the most basic building block of neural network, which is a feed-forward network. As you all know, the regular feed-forward layer, the output is computed by multiplying your input with this weight matrix W. So to add recurrency, we need a mechanism to feed the output back to the layer as an input so that there is a recurrent behavior going on. And we can do it by adding a new recurrent term to the equation, along with the feed-forward term. And generally, there's no closed form solution to this because both now the input and output depends on Z. And the standard idea is to unroll this and update the equation in a repetitive manner. And some of you might notice that this is essentially a ODE formulation of a feed-forward net with the recurrent term. Okay, so how can we optimize this? In the paper, we show that adding recurrency to a feed-forward layer is actually equivalent to adding a sparse reconstruction layer. So I won't go through explaining why this is the case, but in the paper, we show the derivation on the equivalence of the two. What's important here is that recurrency can be achieved by sparse reconstruction of the input by learning this dictionary P that encodes the template patterns of the input signals. How do we solve this? In practice, we can efficiently solve this using many off-the-shelf optimization algorithms like ISTA, LISTA, FISTA, etc. So under this VARS framework, we can show that self-attention is actually a special case of VARS. Here on the left, we are making the dictionary P to be input dependent, notated as the phi and x. And on the right, I'm showing the standard self-attention with the kernel trick applied. If you're familiar with the performer work, which tried to reduce the quadratic complexity to the linear case, this is the formulation that they come up with. So under this, you can see sort of a parallel between the two equations in here. But the difference is that VARS contains this inner loop of a sparse reconstruction denoted by U. So under this framework, we can see that the self-attention does the single-step optimization to the layer without the notion of recurrency and sparsity. And here's some graphical illustration of what's going on under the hood. It unrolls the optimization process where we learn the dictionary of templates from the data and then do sparse reconstruction. And then again, update the dictionary and then again, update the sparse reconstruction in an iterative manner. And during the process, as we do unroll this, we find salient regions and then we tend to repress the noisy background patterns. Here are some more examples. And in practice, we don't need too many steps of sparse reconstruction. We tend to use 3 to 5 steps. As you can see, already by third iteration, the attention maps already highlight salient regions. There's some more example highlighting the face and the hand and etc. So how does this happen? What is the relationship between the attention and sparse reconstruction? This is actually not surprising if we think about how the attention works and how the sparse reconstruction works. The attention, human attention, consists of 2 steps. The first is to group the features into separate objects. And then the second step is to select the most salient objects. On the other hand, in sparse reconstruction, first there's an encoding step of we group features into different atoms in the dictionary. And then in the second step, we select the most salient atom using the sparsity constraint. All right. So we evaluated VARS on a number of different image robustness benchmarks. They contain images under natural corruption, out of distribution, and natural adversarial examples, the examples that are particularly hard to recognize, and then also the standard adversarial attack. And for VARS, the dictionary, how we design it, there are a number of different variants that we can do. Here we test 3 instantiations. One is VARS static. Here we first learn the dictionary before doing anything else. We just learn the dictionary from the data and freeze the dictionary throughout. The idea here is to model the general patterns of the data, the entire data set. The second is the VARS dynamic, which dynamically learns this dictionary per input instance. The idea here is to capture more input-specific information. And this is similar to how self-attention works. And the last, we can always combine different ideas. So here, the dictionary will be a concatenation of the static part and then the dynamic part. So first, we apply VARS on the GFT-net, which was presented at New Rips last year. Here, we replace the multi-head self-attention part with our VARS mechanism. And we can see that VARS improves performance on various corruption scenarios under, especially under for ImageNet-C, which is a natural corruption. And it also achieves a slightly better performance on the clean data set, which means, ImageNet itself is not also perfectly clean. Similar story, we apply VARs to the data efficient image transformers presented at ICML last year and observed similar patterns. We also applied VARs to the robust vision transformers, which is actually presented at CVPR this year. And here we visualize the attention maps obtained from different models, including our 3 variants of VARs, and we are comparing it to the vanilla self-attention mechanism. And under clean image, in both these cases, we get reasonable attention maps. But under corruption scenarios, self-attention starts losing some of the salient regions, whereas VARs remains robust. And lastly, I'm showing how VARs attention maps are interpretable to humans by using the eye tracking data. So first we see input images and eye fixation plot, and it shows essentially which regions humans had looked at. And here are the comparisons between the self-attention and the VARs. And we can see that VARs tend to produce attention maps that are more focused on the salient regions. Okay, so that's the second part of the talk. So I want to wrap up this talk. So first, I started with arguing for why we need holistic video representations and why we need the robustness in learning the representation for holistic video understanding. And then I went on asking these 2 questions. How can we leverage large scale, unlabeled, uncurated data? And I was arguing that the robustness is the key to leveraging large scale data. And then in particular, this symmetric loss functions have good properties to noisy views. And the rinse function, which is symmetric when Q equals 1, presents some robustness against noisy views. In the second part of the talk, I went down to the architecture design perspective. Okay, let's forget about the noisy views and etc. When the data itself presents noise, is there something that we can do in terms of the architecture that can robustly encode the noisy data? And then I was arguing that based on this human attention, the recurrency and sparsity plays an important role. And we propose a new self-attention mechanism that are based on these 2 key properties. I'll end my talk here, and I welcome any questions. Thanks.
So you mentioned that when the data input data is noisy, you found that one is more robust in the that you visualize. I found that actually very interesting. So I'm wondering, so when you analyze the matrix A for to have a connection between all, do you see similar patterns as you described for the do you think that why this is
So if I understood the question correctly, do I see the connection between the neurons learned under VARs compared to the actual brain scan of the neurons?
Yeah, so for example, you have so the input also will be produced with the matrix. You see that, for example, for the neuron has when they have different functions, they have a larger weight in the A or yeah.
Yeah, that's an excellent question. We haven't, but I do aware of a work, Wave 2 VAC 2.0, where they train this large scale speech, a waveform encoder. And then they try to show the parallel between the neural activation in their neural network to the brain scan. And there's a paper that recently posted in our archive. They show the parallel between the 2. But I think, it's finding the correlation between neural nets and brains. It might make sense in certain scenarios, and other cases may not. Neural nets, it doesn't have to really emulate how the brain works. We know that, airplanes don't fly like birds, for example. But yeah, does that answer your question? Thanks.
Maybe might have more brown. General sketch of the object or something like that. But that's one area as a semantic.
Great question. You mean for the second part of the talk? The question is, when we, on the second part of the talk, when we apply the VARs, can you see some semantically meaningful grouping of regions that leads to the attention part? Yeah, I haven't shown it in this slides, but in the paper, we actually did a semantic segmentation task as well. And there are some evaluation results. Sure, thanks.
There's no other question. Our speaker was ready. Now we would like to invite on our next speaker, Arnab. Anurag is a scientist at Google Research, and his talk, the title of his talk is Large-Scale Video Understanding with Transformers. Please.
Thanks. Hi, I'm Anurag from Google, and I'll be talking about some of my recent work on video understanding with transformers. So I guess, as most of you already know, sort of transformers are now the most popular thing in vision right now. And that's because they perform so well across a wide range of domains. And so this, of course, has motivated a lot of our work on sort of transformers for video understanding. So the reason why transformers are so popular is that they scale very well with large data sets in a manner that sort of previous CNNs did not. And so this was shown quite clearly in the regional vision transformers paper, and also like a lot of scaling studies on language models as well. So when we think about transformers for video, there's sort of a couple of research questions that we also wanted to address. And I'll be talking about sort of various ways that we address these problems in the sort of papers that I'm going to be talking about today. So sort of one sort of first question is obviously, how do we develop a good how do we develop a sort of strong transformer backbone for video? And sort of, as is sort of often mentioned, transformers sort of have quadratic complexity with respect to the number of tokens. So this obviously means that building more efficient models is crucial. And so I'll be talking about quite a number of approaches along this line. One other thing is that video is inherently multimodal. So there's sort of RGB frames, there's an audio track, you can extract the speech of the people, there's our optical flow. So it's also like an open question on how we can use all this information that we have. And finally, transformers are sort of quite a generic model that operate on sort of any sequence of tokens. So in the last part of the sort of talk, so I mean, this begs the question of sort of if you can train a single transform model to sort of work on all of these tasks at the same time. And so this is what I'm going to be talking about in the sort of last part of the talk. So first, I'll be talking about sort of an initial work on sort of pure transforms on pure transform models for video, which is called Vivid. So this paper might be a bit old by vision standards because it's like one year now, but I'll still go through it briefly because a lot of the subsequent papers are going to be building on this. So CNN sort of used to be the sort of de facto model for vision, and NLP was transformers. And in sort of quite recently, we've seen sort of like this being sort of bridged together and sort of using transformers for everything. So just on that note, it was perhaps surprising with sort of the vision transformers is that the authors followed attention is all you need sort of so closely. The changes were very minimal, and what really mattered was a sort of the large scale training. because we saw that sort of standard like ImageNet sort of was not enough to sort of train these vision transformers. But the sort of success of this sort of work obviously sort of inspired the question of how we can use these on video as well. So Vivid is sort of extending the idea of VIT to videos. So to sort of handle the large number of tokens that we got to encounter in video, we explored sort of more efficient factorized variants, which sort of split the attention in sort of space and time. And so since transformers are these high capacity models and video data sets are actually quite small, it also means that we have to effectively regularize the model to be able to train on these smaller data sets. And we also have to sort of make proper use of the sort of pre-trained image models too. So as I've sort of mentioned, the transformer is sort of a generic model that sort of operates on any sequence of tokens. So one of the sort of first question is, well, what's the best way to sort of generate these tokens from video? So sort of one very simple approach is just to uniformly sample sort of n frames from video and then just to extract sort of 2D patches from them as sort of done in VIT. And you just have sort of n times more tokens. But sort of what we found to sort of work a bit better and is what we end up using in all the sort of future works that I'll be talking about is to sort of view the video as a sort of a 3D volume and then to extract sort of non-overlapping 3D tubelets from the input volume and then sort of to encode sort of each tublet into a token. So in this case, the sort of temporary information is encoded right from the sort of tokenization process. With this, our sort of most simple model is just to simply forward our spatial temporal tokens through a sequence of transformer layers. So this is basically just following VIT and attention is all you need. So this method actually works quite well, but it's sort of very expensive because as you know, attention has quadratic complexity and there's there's many more tokens here because you've got tokens from each frame. And sort of also the high capacity of this sort of means it can overfit quite easily on smaller data sets too. So sort of because of this, we sort of develop more efficient variants of a model. And they also factorize the attention along the space and time at sort of different points of the transformer arc, at different points of the transformer model. And sort of these end up being sort of different space-time attention patterns. So the sort of first variant which we looked at was to sort of factorize the transformer encoder. So in other words, we'd have sort of a spatial encoder which sort of encodes tokens from each frame independently of each other. And then we sort of fuse all these tokens together with sort of a second temporal transformer. The sort of middle column shows sort of shows an alternative where we sort of factorize the self-attention operation along the sort of space and time axes within each transformer block. And the sort of final thing that we sort of looked at is to sort of modify some multi-head self-attention itself. And so for sort of half the heads, we sort of only compute attention on the sort of spatial axes, and for the other half of the heads, we only look at the temporal axes. And so in all these cases, we're just doing self-attention between sort of a smaller set of tokens each time. And so that's what makes these models much more efficient. So I'm going to skip some of the details on this slide, but in terms of encoding the sort of input, so in this case, there's sort of different ways that we can sort of so there's different ways in which we can use a pre-trained sort of vision transform model trained on images to sort of use in our 3D video model. And sort of if we're careful about how we do this, then sort of using the tubelet embedding is actually better. And so this is what we use in our sort of future works. And so when we sort of look at the different variants of a model, and in this case, we're using the same number of tokens across sort of each model. And sort of for sort of large data sets like kinetics, it's our sort of naive unfactorized model, which works the best. But it's also used the most compute, and it's by far the most slowest model too. And it's our factorized encoder model, which sort of is the fastest and has a good balance between accuracy and speed. But sort of the story sort of changes slightly when we sort of go to smaller data sets like Epic Kitchens, because here the sort of unfactorized model overfits sort of much more easily. And this is where the sort of factorizing encoder ends up doing better in exactly the same setting. So one thing I've alluded to already is that it's kind of important to note that video data sets are much smaller than their sort of image counterparts. So this means you have to regularize the model to be able to train it well. So in all cases, the sort of weights of our sort of transformer are from image models that are sort of pre-trained on ImageNet 21K. And sort of when you sort of train on these smaller data sets like epic kitchens or something, we had to use even more regularization than sort of just pre-trained models. So all the sort of methods that are sort of shown in this table, they actually were proposed independently for training ResNets. And they were also popularized by the DIT paper, which also sort of came out last year. And we find sort of it basically makes quite a big difference. And this is essential to basically training on smaller data sets. So at the sort of time of writing this paper, we sort of evaluated on sort of 5 different sort of video classification benchmarks across sort of a different number of domains. So internet videos is kinetics and moments in time. Epic kitchens is egocentric, and sort of something looks at sort of these 5 fine-grained motion. And sort of at the time of writing, it was the state of the art in all of these data sets. And we got sort of further improvement sort of from pre-training on the internal JFT data set. But sort of one thing to notice is that sort of on sort of what we call sort of motion heavy data sets like something and epic kitchens, our sort of improvement over sort of the previous methods is actually not that large. And when you look at epic kitchens, for example, the verb accuracy, for example, sort of is not better than sort of previous approaches. So that sort of tells us that the image pre-training that we use and that we need to use to sort of train these large transform models, it sort of biases the predictions of the model. And sort of it makes it more difficult to sort of capture these fine-grained motions. And sort of this is actually something we looked at in a sort of previous and that we sort of look at in like the next paper as well, actually. But just to conclude this part of the talk is I sort of talked about sort of a family of sort of pure transform models that we use for video. And we show how we can also train them on on smaller data sets as well. This is sort of like a sort of good backbone to work from for other video tasks. And this is what we end up using in the sort of the next papers that I'm going to be talking about now as well. So now I'll sort of switch to the sort of the next paper. So one of the open questions from Vivid, was sort of how we can sort of model these temporal dynamics better, because we could see clearly that on sort of these sort of data sets which have a lot of motion, it was actually sort of not as great as on sort of image heavy ones. So that's what motivates our paper called Multi-View Transformers for Video, or we call it MTV for short. So the background and the motivation is that we sort of know that transformers are good in modeling sort of long range dependencies because they sort of compute self-attention between all pairs of tokens. So effectively they have this sort of big sort of global receptive field. But on the other hand, if you sort of look at the history of vision, like modeling inputs at sort of multiple resolutions sort of has been a central idea for quite a long time. So this sort of stems back to sort of like using hand-crafted features and sort of methods like HOG. And also many CNN models are sort of multi-scale and sort of have a pyramid structure. So when you have this sort of multi-scale processing in sort of space, it sort of helps to detect objects at different sizes. While sort of if you have multi-scale in time, it sort of helps you to detect events of sort of different durations. So the sort of the outline of this paper is how to do the sort of this multi-scale temporal modeling with transformers. So in multi-view transformers, which is this paper, or AMTV, we sort of create different views of the same input. And we sort of process these different views in sort of parallel with sort of different transformer encoders. And we sort of have these lateral connections between these different views, as you can sort of see by the figure on the right here. And sort of finally, we then have sort of a global transformer encoder, which kind of aggregates tokens from each of these encoders. So we can construct different views by sort of using different tokenizations of the same input. So by this, I mean, for example, we can use small tubelets. So for sort of one view, And so if we use small tubelets, that means we're going to have many tokens. And sort of this lets us model sort of these fine temporal details. And sort of for like another view, we can use much larger tubelets in time, and therefore we'll have much fewer tokens along the temporal axis. And this will sort of help us to capture more global context. So we can use different encoders of sort of various depths for sort of each view. And in fact, we found that this is actually what's optimal in terms of like the accuracy and speed trade-offs. So like in the following slides, when you sort of name a model, for example, if it's B2 sort of S4 TI8, it means that we're using a base transformer for sort of processing tubelets with the size of 16 by 16 by 2, like a small transformer for tubelets of size 16 by 4, and sort of a tiny one for tubelets of size 16 by 8. And sort of the actual transformer encoder that we use, it can actually be any transformer backbone. We use a vivid factorizing encoder in all of these sort of experiments, just based on our results of the previous model. So this also means that if we have as like a single view sort of variant of this model, it's actually identical to the vivid factorized encoder. So one other consideration is how do we sort of fuse the tokens from these different views? So in the paper, we considered sort of multiple alternatives, and the best sort of was cross intention from sort of one view to the other. So in sort of cross intention, it means that the queries are always the tokens from the view with more tokens, and the sort of the keys and values are the tokens from the view with sort of this fewer ones. So as you can sort of see in this table, sort of mean cross view attention works quite the best. Sort of one of the sort of obvious baselines that we thought about this is what if you have an ensemble of sort of 3 different transformers basically, and you can see from the sort of ensemble row that actually sort of performs quite well. So it's quite important to sort of do this fusion sort of within the network. And also when it comes to sort of what sort of encoder we should use of each view, we can sort of see I mean, we can see from this table, it's quite clear that it's better to use the sort of a deeper encoder for the view with more tokens, which I think is quite intuitive and sort of makes sense. But at the same time, we can also see that when you use sort of deeper encoders for the other views, it doesn't really help that much. But it's also much more expensive in terms of flops and runtime and the number of parameters of the model too. So that's sort of what motivates our sort of approach of using encoders of sort of different sort of depths for each view. And so once we sort of stick to this choice, we can see that the sort of MTV models that I'm talking about here are sort of consistently sort of better in sort of accuracy and speed trade-offs compared to Vivid. So you can basically see that it's better to add multiple views in parallel than it is to use sort of a deeper single view model. So basically, if you want to sort of continue scaling these models, it's not always better to just make one sort of big transformer deeper, but to rather use multiple ones with sort of different tokenizations of the same input. So using this model, we sort of able to achieve sort of the state-of-the-art results on sort of a wide range of data sets. So this is what we originally did for Vivid as well. But now this paper is more recent, and you can see that the sort of the sort of methods we comparing to are not always Vivid anymore, but also the other ones that came since then. And you can also see we get sort of improvements from pre-training on larger data sets too. So by default, we sort of have ImageNet 21K, since that's sort of the public data that everyone uses. But when we sort of use sort of JFT, which is an internal Google data set, or sort of the weak text data set, which is WTS, we can sort of get improvements from this bigger pre-training. And sort of finally, for this part of the talk, we also have sort of a recent sort of multimodal extension of MTV. So in the MTV paper, sort of each view, we sort of obtain it by sort of having different tokenization of the same input. But what you can also instead do is just tokenize a different modality instead. So you can have sort of one view being RGB, another view being audio, another being optical flow, and so on. So we actually use this model for the Epic Kitchens challenge, And we sort of presented this winning entry this morning. So yeah, we'll probably have a full follow-up paper of this too. So just to conclude this part of the talk, you can see that sort of processing multiple views in parallel sort of allows us to sort of have better accuracy, sort of speed trade-offs for video classification. And sort of another extension of this is also was also the winning entry of the applications challenge too. And if you want sort of more details about this paper, you can sort of look at the code, or you can also come to the poster session to at the main conference. So now I'm also sort of going to carry on with the efficiency angle a bit, and sort of talk about another paper which we call Token Learner. So I mean, as I've sort of already talked about, sort of transformers are sort of this this generic model that sort of work on a sequence of tokens. But for images and even more for video, it's quite often, I mean, it's quite clear that there's sort of a lot of redundancy in all of these inputs. So in video, you see that, you know, like multiple frames, they often show the same thing. And even if you look at one frame itself, like at an image, many of the patches are sort of redundant. You don't have to, you know, look at all of them to know like what is going on in the image. So the sort of key sort of question that Token Learner is kind of asking is, do we really need to maintain and process all the sort of tokens that we have at each layer of the transformer? Yeah, so Token Learner, the sort of key idea is to sort of adaptively summarize a sort of fewer set of tokens that you have, and then sort of just process those. So as you can sort of see by this animation, in Token Learner, we kind of learn a function that, you know, takes a large set of tokens as input and then returns a smaller set of these sort of summarized tokens. And then that's what we can use in the rest of the transformer. So in Token Learner, the actual method is quite simple. We generate an attention map over all tokens in the sequence, and then we sort of compute the weighted sum of these to sort of generate a single sort of summarized token. So we basically compute this sort of S times, and then we have a smaller set of S tokens. So as a sort of a typical sort of example, if you take a vision transformer on at a resolution of 512 by 512, and, you know, just use a normal sort of patch size of 16, that would give you 1024 tokens. But we find that you can summarize all of these into a very small set. So even just 8 or 16 works quite well. So in terms of how we actually calculate the weights of each token that we use in this weighted sum, there's a large number of options that we can do. So you can use a small CNN network. You can use a set of MLPs as a mixer. We can also do sort of cross attention with sort of S-learn query vectors, which is actually equivalent to what Perceiver does as well, which also came out at about the same time as this paper. And sort of in terms of how to sort of use this sort of Token Learner module, we can sort of insert it at an intermediate layer of the sort of transformer encoder. And sort of after the sort of Token Learner module, the sort of the compute that you use is sort of quite negligible. It's almost sort of zero, because we've reduced the number of tokens sort of by that much. Because the attention is quadratic complexity, when you reduce the tokens by this sort of factor, after that, it doesn't really matter anymore. So, I mean, of course, the sort of an obvious question to ask is, well, where do you insert this token layer? Where do you insert this Token Learner layer into your network? So in this sort of experiment that I'm showing, all of these experiments are sort of done on the VIT-based model with sort of 12 layers. So although there's sort of like a relative index here, that's all sort of, I mean, that's based on 12 layers basically. So if we insert a module sort of halfway through the network, so in others after sort of 6 layers, we can see that we basically aren't losing performance sort of compared to the full model. And sort of the flops sort of used by the network have sort of basically halved, because there's effectively almost no compute after this point. And sort of when we insert it after sort of 9 layers, which is sort of 0.75 as the index, we can actually even improve the accuracy a bit, which was a bit surprising to us, but maybe it suggests that this sort of fit model was sort of overfitting in the first place. And sort of these conclusions are basically like they hold whether you even use as low as 8 or sort of 16 tokens. And you can see from the sort of the first sort of part of this graph that we could also sort of tried adding token learner right to the beginning of the network, and sort of we did not expect that to work at all. Because this is sort of, this was added just after sort of projecting the, so this was added after sort of patchifying and sort of projecting the inputs. But sort of here, the sort of the tokens are sort of like too low level at this point. So at this point, they're sort of hard to summarize into like a smaller set. And you can see that in this case, the performance is quite bad. And this is sort of exactly what you're expecting. So as a network with token learner is more efficient, it also means that it's sort of much easier to sort of scale it up as well. So we can do this by sort of processing more tokens. So for example, you can use smaller patch sizes, or you can use like a larger input size as well. Or you can also add sort of more transformer layers. So you can basically make your model much more deeper because it's basically going to handle very few tokens after the sort of token learner stage. And so we've done sort of both of these in this table. So we've made the model sort of deeper. We've made the sort of patch sizes smaller, or we've, and you can see in both cases, we can sort of improve the baseline. We can improve over the baseline sort of without increasing the sort of number of flops basically. And moreover, when we were sort of writing this paper, we were also getting sort of state-of-the-art results on sort of ImageNet, sort of even outperforming sort of VitHuge, which is quite a bit bigger than the sort of model that we're using, and also sort of the VitGiant on sort of on ImageNet Real. And so similarly, we can also sort of scale this model up to sort of video as well. So in this case, we use the same sort of token learner models that were pre-trained on JFT from the slides before. And then we sort of fine-tune an unfactorized vivid model with token learner that was added sort of halfway through the network. And yeah, so once again, you can sort of, on the sort of graph on the right, you can see that by using token learner and sort of scaled up with sort of smaller patches, we can sort of outperform the sort of vivid by sort of quite a bit. And when we look at the sort of previous state of the art, so by this case, I think by this point, the sort of previous state of the art was video swing transformer, and sort of we could sort of outperform this by scaling up token learner. Yeah, so just to summarize this part of the talk, it's sort of as we sort of intuitively expect, there's lots of redundant sort of tokens and images and video, and we can sort of learn to summarize these into sort of a smaller subset of tokens and only process those. And sort of because these models are more efficient, it means we can sort of scale them up to improve their accuracy as well. And sort of that's what we did for both these images and videos. And yeah, so to find out more, you can also look at the code or sort of read the blog or the paper as well. And yeah, and finally, to the last paper I'm going to talk about is sort of co-train models on sort of multiple tasks and modalities. So yeah, as I mentioned, transformers basically work on any sequence of tokens. And because of that, they've been used in sort of like a wide range of perception tasks. So quite often we've seen that people are developing different transformer models. So one for images, one for video, one for audio, and so on. So one sort of obvious question that came to mind was, well, can we actually have a single network with the same set of weights and that can handle all of these tasks? And yeah, so we call this model polyvit. So in this model, the sort of only task-specific sort of weights that we have are just a single sort of linear layer at the end of the network. Because we basically have sort of a different sort of linear classifier for sort of each task or data set. And sort of for each modality, so in this paper, we looked at images, video, and audio. there's a tokenizer that's shared among sort of data sets for that class. So the tokenizer is something quite simple. It's just adding a positional embedding. It's doing the input projection. So for images, it's just a 2D convolution. For audio, we extract a spectrogram first, and then it's just a 2D convolution on that. And then for video, we use a sort of the same 3D convolution as we did in Vivid, because we found these two bits work the best. But the sort of the main part of the model, which is the transformer encoder, which sort of has L sort of transformer layers, that's actually shared between all the different tasks and all the different modalities. So this basically means that our model basically sort of acts like an L layer sort of VIT for images. It acts like a sort of L layer unfactorized VIT for video, and sort of acts like an L layer AST for audio. So AST is audio spectrogram transformer, and yeah, so that was also inspired by VIT, and that was a sort of current state of the art for audio. So this model saves a lot of parameters because it's basically sharing them across a wide range of tasks. But it's not really going to gain in terms of runtime or flops, because it's still doing a single task at a time. So this is the sort of kind of like the multitask setting in NLP. But I'm just mentioning this because in computer vision, this is not what people usually mean by multitask, because in vision, when people talk about multitask, they usually sort of mean sort of predicting multiple outputs from the same input. So like predicting like segmentation and depth from like the same input. And that's not what we're doing here, because here the model is capable of doing many tasks, but it only does one at a time. So when we sort of co-training with all these different tasks, so one sort of like probably the first question is, well, how do we actually do this co-training? And well, it's how do we do this, and sort of how feasible is it to do? And so the method we use is actually very simple. So although we have sort of these many different tasks that we want to do, for each sort of training step of SGD that we do, we actually sample a batch from just a single task. So there's there's many reasons why we construct a batch from only a single task. So it's much more easier to work with, because now we can actually use different batch sizes for each task, and you don't need to path things and so on. But it also means that you can use different learning rates for each sort of batch that you process, because it's all based on the sort of task that you're doing. And so you can use different learning rates, different weight decays for each batch, and like so on. And the reason why this is important is because this means we can actually use the same learning rate schedules as what we do in the single task baseline model. So it means we don't actually end up tuning any more hyperparameters than what we did for training just a single task model. So this means it actually ends up being very practically useful, because it means we can co-train very easily without having to sort of do these sort of big experiments to see, well, like how do we actually do it? And this actually also means that we actually end up training for the same number of steps as what we did for training sort of n different single task models. And sort of that's useful because we'll compare to these later on. So in terms of like the different strategies that we sort of tried out, in terms of what actually works the best, it's to sample tasks sort of with a weight proportional to the number of training steps in the sort of single task baseline in the single task baseline's configuration. So from the sort of first two rows, you can see what sort of does not work at all is sort of task by task. So just choosing batches from one task and then moving to the next and so on. That was completely expected because that causes catastrophic forgetting, and then that model will only work on sort of the final task. One thing also that does not perform well is accumulated gradients, because when you accumulate gradients from all the different tasks and then do one update step, it sort of forces you to use the same learning rate for all the different tasks. And that's actually quite bad because we see that the optimal learning rate is actually quite different for each task. So for example, for image data sets, we need a much smaller learning rate than for like video and like so on. So it's actually quite important to sort of sample tasks randomly. and to use task-specific learning rates. And also it's important to do sort of more steps for some tasks than others. So when you look at the third and fourth rows, which is sort of alternating and uniform sort of sampling, we do the same number of steps for each task. And sort of this also is not the best because it means that you can train for too long on some data sets and overfit on them. And it also means you can train for sort of too short on others and underfit on them. So that's why sort of sampling or like weighting your sampling is basically quite important for this to work. And sort of now when we sort of look at when doing multiple tasks, we basically have sort of two clear baselines. So one is just to train a model for each classification task. So that's a single task baseline you see on the second row. So we expect this to perform quite well, but it just means you have to train in different models. So it's just more expensive. One other sort of alternative to reusing parameters is just to pre-train a transform model, and then freeze those features and just train a linear classifier on top. So this is actually like a valid baseline to polyvid because it has the same number of weights. But as you can see on the first row, it's easily the worst, and maybe that's not unexpected either. So on the sort of first row below the sort of bar, you can see that when we train a polyvid model separately for each modality, we actually sort of achieve the best results on basically each of the tasks. And when we sort of train a polyvid model for sort of all 9 of these tasks across 3 different modalities, we lose sort of surprisingly little performance. So you can see, so we are actually quite surprised that we can sort of train a model on all of these tasks, and we lost at most 1.2% across all of them. And to us, this was surprising that sort of one model, and this is just a sort of like a VIT-based model, so it's not even extremely large. So we were expecting to lose more, but well, we didn't. And you can sort of reduce some of this gap by sort of adding some modality-specific sort of weights. And that's what we have in the sort of last line of this table. So we added sort of modality-specific layers to sort of to the network. So you can think of it as a deeper tokenizer. That does recover the gap a bit, but we still found it very surprising that we could use one model for everything and basically not lose much at all. Sort of another experiment that we did was sort of train linear classifiers on top of the frozen features that we're getting from a model. So as you would expect, sort of a polyvid model that's being trained on different tasks and modalities, it sort of learns it learns features that transfer across sort of like a wide range of domains. So like it learns features that transfer on other audio tasks, on other image tasks, and on other video tasks. So in that sense, it's sort of like a universal feature. It's like a universal feature array extractor. And sort of as you expect, this is not the case for sort of single modality models. So before I also mentioned that sort of when you co-train on a single modality, it sort of gives improvements across all the tasks. So with this, we can sort of improve on the sort of the unfactorized vivid model on sort of some common video common video data sets. So you can see that we improve the most on sort of smaller data sets like kinetics 400, because this way vivid would otherwise overfit. And you can also see that co-training sort of has a regularizing effect on training, because this is how we sort of end up improving on sort of all of these tasks. And we sort of had the same trend in audio too, where sort of MBT was the sort of state-of-the-art approach on these data sets, and we could improve on both of them. And again, we improved the most in VGG sound, which is the smaller of these audio data sets. Yeah, so just to conclude this final paper, we can sort of see that we can co-train a single transformer to sort of perform these multiple tasks across different modalities. And sort of co-training has a regularizing effect. So when we co-train on like a single modality, we can improve sort of on all of these tasks. And when we sort of co-train on multiple modalities and tasks, we can sort of be extremely efficient in terms of the parameters of a model. And quite surprisingly, we sort of lose very little sort of accuracy as well. And sort of quite importantly, sort of code training is very simple and practical to do as well, because we don't need to do any sort of additional hyperparameter tuning over sort of single task baselines. So I also just want to emphasize that I've had a number of great co-authors in all the work that I've presented today. And if there's any questions, I'm happy to answer them. There's a hand there. Sorry, can you speak a bit louder?
Smaller data with small data different datasets with maybe this kind of second section happens. Have you guys tried out on that or they provide on
Right. Yeah, thanks. These are good questions. Yeah, in terms of the regularizing effects, I mean, it's kind of related to the domain of the data, basically. So basically, we find when you the more sort of similar data sets you co-train on, that's basically the more sort of potential benefits that you could get. Actually, what I didn't have on the slides, but we've done separately, is instead of looking at co-training, you can also say, well, let me just fine-tune a model on like a sequence of data sets, and then it's guaranteed to have seen the exact same amount of data. But even in that case, like it's worse than co-training. So there's basically benefits to basically doing this all at once. And in terms of your second question of whether we've tried other modalities, yes, we have some results on using text as well. We're still working on that, but yes, like I mean, there's no real sort of limit to, I mean, with a transformer, you can tokenize pretty much anything. And yeah, you can work with that.
So I was really impressed by the learner paper. Just to put thought, could this process be like kickstarted? If say you use like optical flow or some other type of information you had about the video to say, you know, bias it early on towards, you know, the highest motion parts of the video or certain objects or something like that.
Right. Yeah, I mean, that's a valid point, but I mean, we could try that out, but I guess sort of one thing is that, I mean, we're not explicitly, I mean, in sort of token learning, we sort of aggregating, you know, one set of tokens into like a smaller set, and you kind of hoping that the network kind of learns it from, you know, from all the training data basically. So I'm just one sort of concern about that is if you bias it too much with your own sort of priors, it might not work I mean, it basically might not work in all cases basically. Yeah.
A really impressive animation.
Yeah, I mean, we basically made a blog post, and Tom Small has written here, like he's the artist who made it. So we quite happy with it.
Maybe we might have a few questions.
Oh, and on Zoom.
Yeah, let's quickly check. Somebody has raised. Do you mind if I stop?
Yeah, sure.
So we have. That's for you. Yes.
Right. So someone is asking, does token word learner work on Epic Kitchens as well? Yeah, I'm pretty sure it would. We didn't try it for this paper. Yeah, I mean, there's no particular reason for why we didn't do it. Yeah, we just didn't have the time. And how many modalities can we train in parallel at max? Which, I mean, I don't know which paper this is referring to. I guess it's on Polyvet. Yeah, for Polyvet, yes. No, I don't think there's exactly a limit, like whether we do different modalities or different data sets. I mean, there's no real limit. We went up to 9 in the paper. but we could have done more. I mean, there's no specific reason because when you look at the training of Polyvid or even the inference, we're only processing one task at a time. So in terms of efficiency, it's the same as a standard vid. So there's no limit from that perspective.
Hi, so I just had a couple of questions.
Yeah, someone has a hand up as well.
Yeah, so that's me.
Thanks.
Yeah, so thanks for the talk. So I just wanted to follow up on a few questions.
Can we not hear them, or are they just not saying?
Hello, am I audible? Hello.
Is it us that's muted or them?
Yeah.
Oh yeah, we muted. Can you just ask the question again?
Yeah, sure. Thanks for the great talk. So I just wanted to follow up on a few questions about Polyvid.
Sure.
So basically, the first one is you mentioned a couple of times the problem of quadratic complexity on the self-attention computation. So for the Polyvid scenario, I would imagine this is like the most acute in some ways. So did you actually consider fusing at multiple levels rather than fusing the modalities at one particular level? And yeah, go ahead. Yeah.
Sorry, can you, I mean, I don't think I completely get you because in Polyvid, even though we're doing all these multiple tasks at the same time, we only, I mean, although the model can do these multiple tasks, we're only doing one at a time. So in terms of complexity, it doesn't change anything according to the then it basically means the number of tasks doesn't have any effect basically.
Right, I see. No, I was just curious because if someone were to implement it on a task where it's multiple modalities at the same time, then that issue might come up, right? Okay.
Right, yeah, I mean, it does come up. We actually have another paper, which I didn't talk about today because of time and because it was in another workshop too. It's called multi-model bottleneck transformers. Yeah, so that's like a more efficient way of using these different tokens. And we did a lot in audio visual tasks. Yeah.
And just quickly, one last question. So why does your Polyvid model not suffer from things like catastrophic forgetting?
Right. So, I mean, catastrophic forgetting is what you would have if we did the sort of task by task schedule. I mean, we actually showed it too. So it is basically, if you have access to all the different data sets at a time, you should use them all during training. If you use them sort of sequentially, sort of one at a time, like in the task by task schedule that we had in the paper, that's how you get catastrophic forgetting, basically.
I see. Thanks.
There's no other question. We would like to thank our speaker again.
Thanks.
So we now move to our last talk of today. So our next speaker is Vishy Swaminathan, Senior Principal Scientist from Adobe. The title of his talk is Enhancing Video Experiences with Contextual Data. He has sent us a pre-recorded video. I'll just share that.
Hello, my name is Vishy Swaminathan and I'm a Senior Principal Scientist in Adobe Research. I'm excited to talk to you guys about enhancing video experiences with contextual data in the Holistic Video Understanding CVPR workshop. So let's get started. Today, there is not only abundance of content, but there is also abundance of data on how that content is consumed. So the pitch I'm going to make is that it is not only important to understand and derive insights about the content itself, it is also very important to understand and derive insights on how that content is consumed by analyzing the behavioral data associated with content. When we do that, that's when it's truly a holistic understanding of the video to enhance the video experiences. Marketing campaigns, as an example, start with content. They are personalized for the audience segments and the context of the users. You start with the content, but you either adapt the content or pick the right content for that audience segment and the context of the users. The assertion I'm making is that if content is king, context is queen. You can go from just content to content experiences by using that. Starting with the videos and using the context in which it's going to be consumed, you create video experiences that the users are going to be delighted with. Without the context, videos are simply consumed, but with the context, videos are experienced. So how do we get there? Today, there is a lot of work around using ML algorithms to automatically understand videos, understand the video frames, understand the audio associated with it. There is also a lot of work around deriving insights around how this content is consumed, whether it's website analytics or analytics around who's consuming what videos, how much time they're spending on it, what parts they're skipping over, views, likes, comments associated with the content, so on and so forth. And that's what I really mean by analytics data here. There is a lot of work around deriving insights in that. The pitch I'm going to make is that the AI ML work that is at the intersection of the two, not just on videos, but also the behavioral data and the behavioral analytics data of how those videos are consumed. When you combine the two, it becomes a lot more powerful, and you can create not just video consumption, but video experiences out of it. So how do you make it an experience? You start with really high quality videos. You deliver them in most cases. You obviously have to have a good understanding of what content is delivered, and you have to understand the context in which these videos are consumed. So how did we get here? Maybe taking a step back and understanding or remembering how bad videos were over the internet, particularly. We used to see buffering all the time, and video experiences not too long ago, about 10 years ago, 11 years ago, used to be pretty bad. From there, we have come to a point where streaming is almost ubiquitous now. You can't even tell the difference between, say, streamed video over the internet or cable providers. In fact, even most of the cable providers now use streaming over IP. So how did we could convert what used to be video consumption to video experiences, or lay the foundation for video experiences by really high quality video streaming. These are the complaints, again, about 10, 11 years ago, at least when I started working on video over the internet. It took a long time to start. It was always behind TV. It kept buffering, and the quality used to drop, frames used to drop. There were lots of from the users around it. So there were, what you see on the left is a client, what you see on the right is a server. Traditional video protocols and arguably the right way of delivering over the internet used to be content over UDP packets and RTSP as a control mechanism on top of it over TCP, where it was very clean. However, there were lots of issues around it. So we moved from those protocols where the servers controlled what quality of the videos were delivered to the client, to clients requesting segments of the video at the quality at which the clients could consume. So you could analyze the conditions of the client in terms of network or compute, or even screen sizes and whatnot. The client started requesting, okay, give me the next segment in this quality. That's all I can handle. So in a nutshell, the client used the context of the client a lot more to improve the video experiences. there were things like even after the quality generally improved, what you see on the top is cable users, and what you see in the bottom is online users. So you could see that they are a good 20 to 30 seconds behind. What would happen is that, I mean, you can imagine all kinds of things in terms of betting and whatnot, where the one set of users got the content, and the event, like a goal, happened a lot more. They would post on Facebook and Twitter, whereas the people who are following that and watching it online, it would spoil the experience for them, if not else. So what you see on the left is a traditional streaming, where each segment of the video is requested and delivered over HTTP. What you see on the right is that it buffers, or it because the latency is so low that it starves. We worked on technologies to improve that, so a single request would preemptively make the server send a lot more segments than just one, to smoothen it out so that there is no buffering at all when you do that, is what you see on the right. We worked on low latency streaming, and several others worked on low latency streaming over HTTP2, for instance, to make those experiences much better. The reason I talked about the previous set of technologies was to say that the history tells us that when the context of the client, in this case, not necessarily the user, is used, the experiences become much better. Our own first generation of video research simply looked at content understanding. So what you see on the left is given a video, we could generate metadata, and what you see on the right is that given a video, we could generate different summaries of that video. And this relied on simply what's inside the content, or traditionally what we call content understanding or video understanding. I'll get a little more into these technologies in the next few slides. So what you see, this is given typically any video, we could generate, in this case, ad specific metadata. So it's not just the actions and objects in the video, but also themes in it. So for instance, you see surfing, but some of the activities, things like outdoor recreation, surfing, and bodyboarding, which may or may not be exactly what's seen in there, but given that this was done in a context of ads, you would still want to match content with ads, let's say. So it is although it's not accurate in terms of objects and actions, it is still relevant to say, to show this video, let's say, associated with jet skiing that's going on. You could even argue whether the accuracy is right there or not, but in terms of ad specific metadata is what is generated. There are, of course, tremendous amount of work in generating objects and actions in CVPR, which I don't need to talk about. The second set of work that I was going to talk about was generating a single summarization engine that could generate thumbnails. So what you see on the top left is a car ad, and what you see on the right are thumbnails / flashcards, which really does a good job of picking different parts of the ad, including there is a flashcard on McLaren. So the difference between thumbnails and flashcards are that as you see in these websites, you sort of flip through the flashcards to show a preview of the video. And there is something called animated thumbnails, which is what you see in the bottom left, which is a 2 second 2 seconds of the video that you show that you would sort of play repeatedly for the different videos available. What you see on the bottom right is the actual summary of the video that was generated. It is quite interesting that for this particular video, the engine came back with not just sort of the inside charts, outside charts, dashboards, but also sort of a end frame, which gave the model of the car. So what we did here, again, this is sort of the first generation of technologies. What we did is that we took the frame level features, which is like most other work in that, we used Inception V3 features at that time. We captured the temporal dependency among frames with the LSTMs. And then we minimized the deep feature distance between the summaries and the original video, or the feature extracted from the summaries and the original video. Maybe I'll skip to the next slide. We used a VAE GAN mechanism to extract frames, to have a selector, and then we use an encoder, decoder, and minimize the distance between reconstructed video frames and the original features. And then the VAE decoder is your generator in this case. And then you have a discriminator which tells you whether it's the original video or a summary, which is a simple binary sequence classifier implemented using LSTM here. I can obviously go into a lot of details there, but maybe what works well is if I show a demo and I can go over the details offline. So this is a different ad. In this case, there is a storyline associated with the video. So it's about an immigrant coming to the United States and then starting a beer company. What you see on the right is essentially thumbnails or flashcards that are picked from the different parts of the video, which sort of conveys the storyline. What you see on the left is a 2-second version, which is arguable. The 2-second versions are always arguable in terms of whether they convey or not. What you see on the right is a summary of the video itself. As you can see, there are parts of the story that are captured. The good thing about this particular demo is that you can change the duration, and then it automatically generates summaries for those durations. And then, particularly, we looked at ads as one of the things that we wanted to work on at that time, and it did a really good job on different types of ads. This was one of the harder ones, but there were other cases where we felt it was doing even a better job. But even in the harder cases like this, it did a decent job of. The second generation of video research, at least in our lab, was looking at the consumption data. So in this case, we did not look at the video data because it was just not possible to do recommendations. At the same time, looking at the visual data, there was a possibility of using pre-generated metadata or hand-coded metadata along, but not in real time at least. So here we use consumption analytics. So for instance, instead of while recommending videos, we look at we want to make sure that we recommend the right video, not just based on a user ID and the past history, but also personas within a single user ID and the context. So in a nutshell, what videos I want to be recommended, let's say I'm watching with family on my Apple TV, is very different from my own user ID when I'm in, let's say, in the park or on a holiday and the kids are watching it over iPad. Or what I'm recommended on my morning commute to work. In the first case, it's family, and the second case, it's it's kids, and the third case it's short videos, maybe for what I can watch or catch up on news, things like that. So what we use here is not just any metadata that you have about the data and the users, and also that we have this problem that ratings are not going to be possible for non entertainment video typically. So we have data around how much of the video was consumed by the different users, and we have some associated metadata about the users and content metadata associated with the content. We put it all together. We use how much of the video was consumed as a proxy for a star rating. So if 75% of the video is consumed, we consider that to be 3 out of 4 stars. 50% is 2 out of an equivalent is what we use. We actually have a continuous scale instead of a discrete scale like that. And then what comes out of it is not just personalized recommendations, but also recommendations that are adapted for the time of day, for the device, for the location and geo. We use a factorization machines algorithm to feed all of this context data, and to use the context data and not just to do straight collaborative filtering between users and items to get recommendations. Again, the context in this case can be pretty rich. It could be content metadata, include content metadata, but also users, data, device, some amount of consumption analytics, like what videos you watch, how much of it you watch, and any third-party data we have. An example of somewhat boring contextual data is in this is shown here, where it's number of videos watched, who your carrier is, what your domain is, or the domain of the video that was watched, geo, things like screen orientation, whether you're landscape or portrait, who the author of the video is, the section or the category of the video, and how many times this user has visited this particular site. If you throw all of the kitchen sink in it, in this case, there were 171 different context features. You see certain RMSE, which is somewhat worse than not using context at all. But if you use the right context for this particular case, we see that there is significant improvement over not using context at all, even using factorization machines algorithms in this case. So what we learned here is that the context is super important. However, the right context is important, not the kitchen sink. So here's an example of a demo, a mobile demo that we had at that point, 4 or 5 years ago, where what is really shown in this is that as you change the user from John to Jane, the recommendations change, and remembering that as you click on these videos, it doesn't take any time. It's almost like switching channels on your TV, that it starts instantly. So what we did here is that we pre-buffered some of the videos that were recommended, so that you can immediately start without any startup delay. So in this case, we understand, we deliver the video at the highest quality, for instance, and make that experience TV-like, and recommend based on context. Here's another example of how we use the context. This is, say, a 9 a.m. Is changed from 9. When we change from 9 a.m. to 9 p.m., you see that what was short videos became long videos that are possible, and what you also see in this case is that when you change from iPhone to iPad, you could replay some of the things that replay some of the games that happened that day. Let's say this is in the context of Olympics. Whereas if it was iPhone, you see highlights, and if it's iPad, you actually see you get recommendations of the replay, which makes sense. If I want to rewatch a game, I'm less likely to watch it over my iPhone as opposed to an iPad or an Apple TV. The third generation of data, third generation of video projects in our lab is actually combining content understanding or traditional video understanding and using the consumption analytics at the same time, or behavior data analytics at the same time. An example of that is the watchability project, which I believe that the research should be in the window of scarcity. This is not something I came up with. Window of scarcity or research in window of scarcity has been around for some time. You don't want to do things that are impossible to implement. You don't want to do things that are too easy to implement. The window where just pushing the line between impossible and easy is where research should be. And I believe that research today in the video space is a combination of video understanding plus using insights from how that video was consumed. So, for example, this is an example of an Old Spice ad, which was super popular, and the visuals were good, but it was, at least for me, it was a bit difficult to understand why this ad was popular. Whereas this ad, the previous one was an Old Spice ad. This is a Pepsi ad, which was really nicely done. However, this ad was not successful at all. Now, the biggest challenge we have is that, and in both these cases, the visuals were great, the audio was great, the music was great. It had very popular actors in the ad itself, as you may recognize. Is there a way to build a machine that can predict whether these videos are going to be successful or not? So this is the sort of the high level problem that we set out. Today, videos are created and users interacted with those created videos. We have that data. Can we feed it to a bunch of ML algorithms and figure out how effective these videos were or how watchable these videos were, and can we feed that back to creators as they are creating these videos? So we said, let's figure out how to do this. We take the video, we take the audio, and any associated metadata. Remember the first generation metadata or ad metadata projects we used. So we said, okay, we can take an ad, feed that, take that video frames, analyze the features, take the audio, analyze the features, take any associated metadata and also analyze that. And then we came up with a mixture of experts model to give a watchability algorithm out of it. And I'm happy to go into the specifics of what we did in the different in the different modules there. But at a high level, it was LSTM, a fully connected neural network for audio and logistic regression, a very simple logistic regression model to take in the metadata that was available with the app. So let's see watchability in action here. This is an example of an ad that some of you may remember. It's a Tide ad, which is very effective. Our system came back with a watchability score of 5 out of 5, with a confidence of 72% for this. In my opinion, the ad is a little bit annoying. It's essentially that the stain speaks to it's so distracting that the person who's interviewing this candidate feels like that the stain is talking to him and is not able to focus on the candidate's answer. Then it's super effective. And interestingly, the system came back with a 5 out of 5 and a pretty high confidence on what the watchability score is. Here's another example where the visuals are fantastic. It's a cocktail making ad. The audio and the video are just simply really nicely done. However, the watchability is 3 out of 5, with a slightly lower confidence, but the effectiveness of the ad itself is just 3 out of 5. 3 is slightly above average, or about average. Actually, in this case, for this data set, 3 out of 5 is about average. It was, and this is very similar to what the users had rated this ad to as not so effective in terms of the message itself and whether they liked the ad or not. We talk about 3 different research projects. So let's see what happens if you put them all together into a single system. We developed this for ad-based technologies. Let's say you have a video ad that's ready. You drop it into the system. It analyzes it for you and generates ad-specific metadata. So the video itself is about surfing, and as you let the system generate metadata, it generates, as you can see, keywords which you could use to put this ad along with other videos that people may watch about adventure or water sports or even vacation. What you see on the right is that, so if I show this ad in TV as opposed to Instagram as opposed to Facebook, how well is this ad going to do? It takes in so we let our watchability algorithm loose on this ad. It takes in of course, the audio and the video, and in this case, the generated metadata, and analyzes it with of course, it uses historical data to come back with. Let me go back here for a second. To come back with the watchability scores. So as you can see that the watchability score on TV and Facebook is pretty high, whereas for the Instagram channel, it's not that high. We all know that ads that work well on TV don't necessarily translate to working well on social channels. I'm talking about video ads. The reason for that could be, the demographics are different, the expectations are different. But in this case, we can actually tell why, because the ad itself is about 107 seconds. And that's just way too long for your Instagram audience. If you don't know why, you should meet my kids. In terms of the expected attention span for the Instagram audience is not that long. And the watchability algorithm itself did really well to figure that out. It doesn't tell you why, but it tells you that the watchability is going to be too low. So what we said, we give the option for the marketer to automatically summarize this video to different durations. So we used our summarization engine. When it goes all the way to 0, you can see that it generates fairly good thumbnails of beautiful scenes and even animated thumbnails and flashcards. If 15 seconds is the right target for the Instagram audience. So what you see on the top left here is that it's generating a 15-second summary of it. It takes a little longer than the demo itself to generate the summary, but as you can see, there are some outdoor scenes, there are some talking heads, and then ends with a sunset scene and even with the name of the brand of the travel brand that we were trying to do in that. What you see on the top right is that the watchability score has been recomputed, and what was 20 with a lower confidence of 50 or so has become 90 with much higher confidence when you sort of fed that back into the watchability algorithm. So while explaining that system itself, you probably think, can you not close the loop? Why should a user figure what the duration should be? So we said, okay, so can we put all of these pieces together create variations of the original content and iterate through till you get the best best predicted performance, in this case, watchability. So we said, okay, you can, start with the watchability score somewhere in between and imagine a surface and iterate through. So we generate, variance, and then you incrementally keep the best performing variations at the top three is what we did as intermediate representations. And with the highest watchability score are kept as survivors, and then you let the algorithm iterate through a combination of generating top three variants and keeping the top, generating the variants and keeping the variants to make progress. So when you can't make any further progress, you stop and pick the one with the highest watchability score of the three remaining survivors. So here's an example of an ad that we used. Some of you may have seen this ad before. I won't play the entire ad, but it's got some, inside scenes, outside scenes, some dashboard scenes that show the feature, and eventually finishes with the model number and whatnot. So what you see on the left here is one that was generated by our algorithm when you select a duration. What you see on the right is something that it automatically figures the right duration. So what you can see on the left is scored a watchability of 3 out of 5 with a somewhat of low confidence. What you see on the right iterated through till it got the best confidence. You can actually tell that it captured the main aspects of the ad, including the model number and the price, and the performance was actually good. And you can understand why the watchability score was high. So let's switch gears and talk briefly about 360-degree VR videos and how context is even more important when you have 3 degrees of freedom and 6 degrees of freedom along with your videos before we end. So the simple difference in 360-degree videos is that with a head-mounted display, you see only part of the video and you can actually explore with 3 degrees of freedom. So this may be the original video, but what you see is really low quality because you have to stream the entire video, with available bandwidth. So tons of the rest of the video that you're not watching, you can consider it as wasted bandwidth. So the difference between 360 and traditional video in size is an illustration that's shown here. One option to do that is one option to solve this problem is you tile the video, you predict not just see where which tiles the user is watching, but also predict which tiles the user is likely to watch in the next few seconds, and send those and just those in high quality as opposed to the entire video in high quality. You would still send the other tiles because user can turn around and see other parts of the video, but they would be at a lower quality to improve the overall performance of the VR video. So here the difference is that how a user moves from one tile to another is not just content specific, but also user specific. And how good your prediction algorithm of what the user is fixated on right now to what the user is likely to watch in the next few time instances, and how well you predict that will directly determine the overall experience of the user. So in some sense, it's a context to the user on steroids, and how you have to react much quicker in 360-degree videos because of the 3 degrees of freedom that's there. So simple algorithms include, you take the current head position and the speed at which a user is moving to determine the future position, but you can do much better than just that based on content, based on the user itself, is because some users move really fast while other users move fairly slow. And then you can use the network protocols that I talked about before to push the tiles at higher quality. And so I show a quick demo here. This is the traditional VR streaming, where you see that the quality is generally a little low. I won't play the entire demo, but the overall quality comes down considerably. You improve it with tiling. So here what happens is that as a user moves around, if you watch it really closely, and since you have the video, you can probably watch it closely, you see that when the user pauses, it pops from low quality to high quality as the user moves around. When you not just tile, but also use viewport prediction, you can see that the higher quality that you see in the different tiles is actually very smooth, especially when the head movements are predictable. In this case, it's a fairly smooth head movement, so it's actually predictable, and you see that the quality goes up considerably. Here, it's again, different users explore the scene in different ways, so you have to predict it, not just based on the content, but also based on the characteristics. So what does the future hold? So as you can see, even today, most of the car ads are not shot with the actual cars that are in the video, like you see in this example on the right. The future is that based on data, based on segments, different videos can be automatically generated or shot. And eventually, when you get to a segment of one or completely individualized videos, you can't actually create those videos at that scale. It will be automatically driven from data. So you would have data-driven variant generations from the video. It may not be for all types of video initially, but that's where the future is. Again, I'll leave you with most auto ads are today computer generated, and similarly, volumetric videos will combine 3 degrees of freedom in VR along with AR, which is 6 degrees of freedom, and it's really hard to tell. And even in this example, it's sort of hard to tell what's real and what's not. But hyperrealism in 3D content, including videos, is coming. And context is even more important for some of those. And here are a couple other examples of volumetric videos in actual spaces. So it's volumetric videos within videos. And that's how future video experiences are likely to be. So I leave you guys with, video obviously have to be at high quality. The more you understand the content, the more you understand the context, you can convert what is video consumption to video experiences. Content is king, context is queen in this case. You can argue which one is more important. All of the work that I showed today was done by this team, starting from Science, Somdev, Gong, Holiang, Stefano, Shang, and Kanak, and some of the members who have who were part of the team at different points in time, whether they were interns, visiting faculty, or past employees. Han, Gwendol, and Sheng were contributed considerably to the demos that I showed. Thank you, and I'm happy to take more questions.
Hi, Vishy.
Hey.
Thank you for a fantastic talk. It was amazing. So, I think so. From my end, I had one question. So, because you showed so many nice use cases and like really applied sense, because more than just academic research, like you had really interesting use cases where what's going on. So I was curious, like from your aspect, like what do you think, what's next that I'm thinking, like what's going on, and what do you think, what are the next things that how the field is gonna progress, or like from industry/academia perspective, and where are we gonna head to?
Yeah, I mean, that's a fantastic question. I don't know if I have an accurate answer for that, but I can give my views on it. I think from the research community in video understanding, the tremendous technologies that are coming out. I do think that we are not necessarily working on real-time understanding enough, and especially for some of the use cases I mentioned, where you could create a video ad particularly, and how somebody in the West Coast may see would be different from how in the East Coast of the United States may want to see. How I don't want to say necessarily individualized yet, but eventually it could get into audience segments, and from there smaller and smaller segments to become individualized ad or video. One of the pipe dreams, even entertainment video that folks have, is that content could automatically change based on what you would want it to be. It is arguable whether what role does creativity play in that, and what role can a machine play. But there are very useful use cases that we can solve in between, and a lot of them would require not just understanding of the video, but also doing it in real time, and using the sort of the context of the user. I think, in different directions, there are likely to be different advancements, like VR videos or 6 degrees of freedom videos are all very interesting future directions, I think.
Right. Thanks. If there's no other question in the room, then we can thank our speaker again. Thanks, Vishy.
Thank you. Pleasure to talk, and thanks for the opportunity.
Yeah, you're welcome. Sit. Bye. Sharing. Open. And finally, that's the end of our session. So thanks again, everyone. And we thank all the speakers again, and we thank all the attendees. And our video will be shared online in near time soon. And enjoy the conference. Fantastic.